Okay, welcome everyone to the ICPE 2021 All Access. This is the Pharmacoepidemiology course. And this is John Seeger speaking, and I'm going to be one of your presenters today. And I'm the Chief Scientific Officer for Epidemiology at Optum, and I'm based in Boston. And my co-presenter is Jeremy Rassin, and I'll let him introduce himself.
Good morning, good afternoon, good evening. We'll get to that in a second, everyone. As John said, Jeremy Rassin, President and Chief Science Officer at Aetion, a software company in New York City, New York. And so what we often do when we do this course in person is as people are filing in, and I think we're sort of virtually filing in at this point, see the numbers bouncing around a little bit, and we have a little contest for who traveled the farthest. And John, I have not thought about the rules of this contest in a virtual world. So maybe our origin point would be Seattle, where ICPE was contemplated to be. So who and this is a chance for everyone to get to use the chat and exercise that muscle. Who believes they are farthest from Seattle, Washington on the West Coast of the United States? Anybody want to throw their name in the chat with a me and a location? Brussels, Switzerland, Belgium. Okay, I don't think Baltimore is going to win that game here, but Switzerland is probably the current winner.
Wait, see if anyone's joining from the Seychelles.
Yeah, well, so we have Switzerland, but we have Geneva, Switzerland. So I don't know. Zurich would probably outrank Geneva, I would say, on this one. Finland. Oh, Finland. I mean, given the northernness of Finland, it would be hard to tell. So I have a website that I use that adjudicates any open question. It's the Great Circle Mapper, where you get the Great Circle distance between two cities. So as we start the course, I will work, as I'm listening very, very diligently to what John is saying, I will also work to adjudicate the potential winner. Oh, Taiwan might just take the cake on this one. And a very good evening to our friends in Taiwan and other parts of Asia. Okay, John, should we get going?
Yes, let's do that. All right.
So I'm going to kick it off, but actually you're going to kick it off with a disclosure, and then I'll kick it off with my disclosure, and then we'll start talking about pharmacoepi.
So I'm John Seeger, and I'm employed by Optum, but I'm also adjunct faculty at Harvard School of Public Health.
As I mentioned, my disclosure here is I'm an employee and co-owner of Aetion, which is a software company for pharmacoepidemiology based in New York City, where I am sitting this morning. Okay, so now we are going to get into propensity scores. And so you have the deck. I want to just let you know from the beginning that we will use most, but probably not all of the deck. There are some topics, especially towards the back, that we put in that we use as the class and spirit guide us over the next hours. So if you're sort of counting the slides and seeing that we're not hitting that very last slide, that's okay. That's entirely by design. And we have some extra slides in case there are questions in specific areas. Speaking of questions and speaking of questions in specific areas, please share your questions with us. I think one of the really nice features of these virtual meetings is the chat platform. And so while I'm speaking, John will be monitoring the chat and vice versa. And my colleague Olivia is also online to help us navigate the chat and any other kind of electronicness as we go through the content. This morning, I'm going to say morning because it's 8:05 a.m. here in New York City, but I understand that that's not everybody's experience. So please use the chat, put questions there, put comments there, and that's a great way for us to have a conversation about propensity scores that's most reflective of your curiosity, specific curiosities on the topic. Okay, We will have 4 hours, just one more bit of logistics, 4 hours, and we will take a break in approximately 2 hours. We'll find a good stopping point and take a solid sort of 10 plus minute break, depending on how people are feeling. But John and I chose this live format. We really like teaching the class live. We really like being able to interact with everyone. And so please, let's make this an interactive 4 hours together and get to the bottom of these things called propensity scores. And with that,
and as Jeremy says, it's a course that we want to be useful to you, the members of the audience, and it's not for our own gratification here. It's about what is useful to you, and our experience over the last several years teaching this course has been that there's a variety of attendees in the audience, people at many different levels of experience with propensity scores, and so we have to sort of teach to all those different levels. And part of the way we do that is by listening to your questions and reacting to them, and hopefully by doing that, we'll make it useful to all of you.
Great. So I'm navigating 2 screens here. Just okay. Here we go. Causality. So why are we here? We are here in part because one of the things that we would like to accomplish in our research is a notion of being able to measure and determine a causal effect. And when I say our research, I mean the research that led us here to the propensity score course to determine how propensity scores can help improve that which we do. So what is causality then? Causality, I'll use the Rothman and Greenland definition from Modern Epi in 1998, which despite its 25-ish years ago, still feels like very much Modern Epi. Cause of a disease event is an event, condition, or characteristic that preceded the disease event. Okay, and note the time aspect there, and without which the disease event either would not have occurred at all or not have occurred until some other time. So it's a pretty sort of basic notion of causality, with this fundamental notion of time and longitudinality built into it. That's not specific to propensity scores. That's very much specific to the field that we work in Epi and its related fields. On the next slide,
Trade to advance. There we go.
We think of causality in the context of drugs, which now gets closer to our field of pharmacoepidemiology. Does drug A lead to different outcomes, better or worse, depending on what you're looking at, than drug B? And one way to determine that is to look at, say, a case report and see that patient number 1 took drug A and they had outcome X. And then you say, okay, well, they took drug A and had outcome X. What would have happened if they took drug B? Would they still have had outcome X? So you take your observation that they took drug A, had outcome X. You run over to the closet and you find the little plug adapter that you need, and you plug in your time machine and you rewind time. And instead of giving the patient drug A, that patient gets drug B, and you determine if they still would have gotten outcome X. And from that exercise that you've done, and you're going to have to pay the power bill. The time machines aren't free, right? You can determine whether drug A caused drug X. Now, of course, that doesn't work. You can't give someone a different drug once they've already had a drug. And so we need to find other ways to answer this question. And I'm sure you know of many ways to answer this question. The most obvious one that we come across in our field is ... Does anyone want to throw it in the chat? I'll give you a hint. It's on the slide. It starts with the word R. We're just building some practices here over the next hours, because it would be great to really have a conversation with everybody, as John and I were saying. The most common way to determine causality, or maybe the most obvious way, or the most, I don't know what the right word is, yes, is rand or randomization. Even if you spell it with an S, I think that's exactly right, randomization. And that works because you flip a coin. You have a group of patients, you flip a coin. Heads, you get treatment A, tails, you get treatment B, heads, you get treatment A, heads, you get treatment A, tails, you get treatment B. And because this process of selection of who received drug A and who received drug B is by design totally independent of every single characteristic of the patients that you're studying, you get balance between the treatment groups. It just happens. It's a nice thing. We can also compare everybody who got drug A versus everybody who got drug B. And that works sometimes and doesn't work other times. And why does that tend to not work? It's a word that we come across a lot in our field. It starts with C. And it's exactly that. It's confounding. And so if there is confounding, if there is associations between the treatment and the exposure, or treatment and the outcome that depend on exposure, you have to deal with that. And some people would say on the next slide, well, we're stuck. We can't use observational data, non-randomized data, real world data, kind of all words that I would say are sort of functionally equivalent for our purposes here to understand causality. But let's think about what understanding causality really means. I love this figure from Pearl and Mackenzie's Book of Why, Judea Pearl, based out of UCLA. And they say, when thinking about drug safety and effectiveness, there's 3 levels on this ladder. And the slides go top to bottom, but the ladder goes bottom to top. The first level is associations. Associations are obviously these connections that we see in the data. Those let us generate hypotheses. Interventions at the next level let us test whether a drug caused a positive or negative effect. We intervene, drug A versus drug B. We see what happens. If we randomized our intervention, we can get a sense of a causal effect of that drug, positive or negative. Counterfactuals at the third level let us think about why a particular positive or negative effect may have occurred. But I would argue that the work that we do day to day, by and large, falls under this second category of interventions, and we want to understand the causal effect of an intervention. Now, on the next slide, when I asked how we do that, very many people jumped in the chat and said randomization, RCTs, things like that. And I agree that that is a very good way of doing that. But I want to read this statement by Pearl and Mackenzie very carefully here, because I think it really sets us up for what we're doing here in this course over the next couple hours. What is more interesting and less widely known is that successful predictions of the effects of interventions can sometimes be made even without an experiment. And randomization is an experiment because you flip the coin and depending on heads or tails, the patient gets drug A or drug B. That's an intervention, that's an experiment. A sufficiently strong and accurate causal model can allow us to use rung 1 observational data to answer rung 2 interventional or causal queries. And without the causal model, we could not go from rung 1 to rung 2. So on the next slide, what we're doing here with propensity scores, and we'll talk a lot of different ways of looking at propensity scores, but this is a very fundamental one. Propensity scores are one way to establish that, quote, sufficiently strong causal model in observational, AKA real world data. And they work just like randomization does in that they create balance among the treatment groups, allowing for a fair comparison from A to B. Now, they get to balance in a very different way from randomization, and we'll talk all about that. It's very important to understand that propensity scores aren't randomization. They're an analytic method to get you to balance, but they get you to that point where you can make that comparison between drug A and drug B and the effects of whatever outcome you're looking at, and do so in a way that's fair, and that can start to establish causality. So that's rung 1, if you will, of what we're doing here in propensity scores today. Next slide. So John, over to you.
Great, thanks, Jeremy. And you know, we've talked now a fair amount about causality to begin with this presentation, and in large part because propensity scores go hand in hand with causal thinking in terms of a causal model. You impose a causal model on whatever data set you're planning to analyze, and the propensity scores help you resolve certain aspects of that causal model. And so it's not just an analytic technique such as calculating a mean or standard deviation. It's an analytic technique that really goes along with a study design that leads to a causal conclusion. And one of the main things you're trying to address is what we've already talked about, confounding, is this imbalance among treatments. People who get treatment A may differ from people who get treatment B for a wide range of reasons. And if you talk to prescribers, you can probably get a list of things that might be coming up under the explicit column of things that lead prescribers to choose drug A over drug B. Such as the indication for drug A or drug B, or subtypes of that indication, how sick the patient is, what other illnesses they have, and other medications they are taking, and also maybe any contraindications the patient has. So this list could be, you can talk to a prescriber or talk to several prescribers and generate this kind of list for essentially any drug or any pair of drugs that you're looking to compare. There are other things such as access or practical reasons why a patient might not be able to afford or not be able to use a particular medication. But in addition, there are often reasons that maybe a prescriber wouldn't even be able to point to, but subconsciously they take into consideration when prescribing a medication. And these have to do with how connected a patient is to the medical system, and also training and background of the prescriber. There can be very strong regional treatment patterns. And then, this is an incomplete list, and I'm sure you can think of other reasons that might lead to imbalance between who gets drug A and who gets drug B. But the combination then of explicit and implicit reasons can all represent potential confounders, so that they, if any of these reasons that preferentially selects drug A versus drug B for a given patient also leads to a difference in the risk of an outcome, then it's confounding. And so that a comparison of drug A to drug B will, the effect of drug A relative to drug B will be a combination of the actual effect of the medication and these confounding variables. So it'll be a confounded effect measure that you have. And this sort of diagram, the triangle of confounding in epidemiology sort of reflects that there's a treatment, A or B, that leads to an outcome that's potentially different, X or Y, as Jeremy outlined. But there's an alternate explanation, such as any of these variables that are listed here that change the severity or prognosis or comorbidity of a patient so that they have a difference in outcome. That's a mix of the confounding variables and the treatment effect. And see, random allocation cuts the association between your confounding variables and treatment, so that treatment is assigned by the random number rather than any characteristic of the patient. And so it's really easy to get an assessment of the treatment effect on the outcome. And so what we're looking to do then is find something that can sort of serve as a stand-in for randomization. Because we can't always randomize. There are often resource constraints. Randomized controlled trials take time and cost money, but sometimes there are ethical considerations that say we don't think it's appropriate to assign treatment due to a random number when it overrules clinical judgment. And then sometimes it's completely unnecessary. If there's a very dramatic effect or very clear physiology, you don't need the random allocation to demonstrate the effect. But fortunately for us as observational researchers, the prescribers tend to vary quite a bit in what treatment they select, even when patients have very clear indications for a particular treatment relative to another, there are often a range of variables that go into that selection process that differ across physicians, so that you can find variation in exposure even for patients who have essentially identical characteristics. And so you can exploit that variation to make inferences about the effect of the medication. So we can use the observational techniques that we have at our disposal, which are restriction, adjustment, stratification, matching, and weighting. And if the patients who receive treatment A are different in age from people who receive treatment B, you adjust for age. But what if there are a lot of variables that are part of why people select treatment A versus treatment B, and so that you'd have to account for a lot of different confounders to achieve balance. So one approach, I mean, matching is actually a really powerful technique. It's very intuitive, and so I can walk through this example where, if you find a person who receives treatment A, who has a set of characteristics, they happen to be male, age 45, they're a smoker, they have hypertension. You find a person who has exactly the same set of characteristics, a male, age 45 smoker with hypertension, who also receives treatment B. You could compare treatment A to treatment B for that pair of patients, and there won't be confounding by any of those variables. The problem with that approach is that it breaks down pretty quickly. After you go beyond 3 or 4 variables, and I have this example here with age, we have 10 categories of age, say deciles, and sex, male, female, prior diagnoses, 5 different diagnoses, yes, no for each of those, 5 different drugs, yes, no for each of those, and just your preceding cost of care divided into quintiles, and you have 5 categories. Just that limited set of variables will give you over 100,000 matching groups. And so you find somebody in one of those matching groups who received treatment A, there's nobody else in that matching group. And so that you lose that patient when you try to match exactly on all of these characteristics. And that will happen to a lot of your patients. There'll be some that match probably, but a lot of patients will drop out of the analysis. And so this exact matching breaks down at that point. Okay, so maybe there's an alternate approach. Instead of doing exact matching on all of those variables, what if we come up with something that's a summary of all of your confounders, so that you in effect can remove the arrow, the effect, the association between confounders and treatment, using a single variable. And that's what propensity scores are in a single sentence. A propensity score is a person's probability of receiving treatment given his or her characteristics, everything that's known about. And that's a real world way to say propensity scores. There are lots of implications of it, and we'll spend time talking about some of those. But there's a few observations based on this. And the first is that a propensity score is a number. It's a probability. So it ranges between 0 and 1, as any probability does. And it's estimated from what is measured, what is known about a person. That is, if there's something that's a characteristic of a person that's not known to the prescriber, then it couldn't have gone into the treatment selection unless it's correlated with something that is known. So if you have a propensity score built on things that are known about a patient, that should be sufficient. Back to the causal thinking, this is a sufficient and accurate measure of the causal structure leading to the treatment selection. And so then if you match or condition using other approaches, so weighting, stratification, modeling, all of that will remove or serve to remove the confounder treatment association. Another observation about the propensity score is it's a probability, but it's not an absolute probability. It's a probability of selecting A versus B. It's not not the absolute probability of receiving treatment A. It's always in this kind of relative consideration of whatever you set up your study design is a comparison of A and B. Then the propensity score is those relative your probability of receiving A relative to B.
Yeah, and what John just said is really important. It's in this artificially confined universe where A and B are your only two choices. So given that these are your only two choices, and given that a patient will be treated, what's the probability of A? What's the probability of B? But that is an artificial world, but it is a world that's very much analogous, if you think about it, to the world of a randomized trial, where everybody enrolls in the trial. They've chosen to be in the trial, and then they will get one of the two, and keep it simple here, one of the two trial treatments. So our propensity score is very much in that same kind of logic of the experiment.
Great, thanks, Jeremy. So restating our problem, we want to compare two treatments with respect to an outcome, but there's confounding. That is, these therapies haven't been administered to patients at random, and there are substantial differences then between people who receive treatment A and people who receive treatment B. And these differences are on things like your underlying illness or the severity of the illness. And these prognostic characteristics influence the choice of therapy. So the different therapies are associated with different risk of outcomes, regardless of the effect of therapy. So there's a range of ways to deal with this. So certainly in observational research, we have all of these tools at our disposal to deal with confounding. So there's a set of techniques for dealing with measured confounders off to the left here. And those are restriction, matching, standardization or weighting, stratification, and multivariate regression or modeling. So those 5 techniques are the ones that we're going to be talking about. There's a whole other set of techniques that are used for unmeasured confounders, and those are outside the scope of what we're talking about, because propensity scores really are ways to deal with measured confounders. They only help with unmeasured confounders to the extent the unmeasured confounder is correlated with something that is measured. And so this measured confounder side is what's amenable to propensity techniques. Okay, so more on propensity scores. They're really thought of as a 2-step process. First, you need to build it, and then second, you need to use it. So use the propensity score. And there's a fair amount of work involved in each of these two, and we're going to sort of divide the course into this using this approach. To begin with, let's build a propensity score, and to do the building of the propensity score, going back to that causal model, we want to include in the propensity score the variables that the prescriber actually used in their decision to apply treatment A or treatment B to a particular patient. And so you want to, I've already mentioned talking to prescribers, because it helps inform why they select one patient or another. But without prescribers, I mean, you can also go to clinical practice guidelines about what types of patients should receive one kind of treatment or another kind of treatment. How do you treat condition X? There's a set of practice guidelines potentially that you can go to if those have been developed, and that will give you a pretty good idea of what variables should go into your propensity score. And the other aspect, though, is because you often have a situation where many people are treated with treatment A or treatment B, you can build a very rich model of prescribing. So you can say, okay, we have hundreds or maybe even thousands of patients who receive treatment A and treatment B, and you have more people who receive those treatments than actually have the outcome. So if you're looking at strokes or myocardial infarctions, only a subset of your starting cohorts will have those outcomes. And so if you're building an outcome model, there are much fewer people who have that outcome, so you can't build as rich a model. So that's one of the advantages of propensity scores, that you can build a really rich model of prescribing and use that to address confounding, even for a rare outcome. So then you collapse all of those variables into a single variable, which is a predicted value of treatment A selection versus treatment B selection, and that's your propensity score. And then you can use that propensity score. And remember, the propensity score ranges between 0 and 1, and it's very much like other other variables that might range between 0 and 100, 100%, such as age. And you can really think of as any way that you could use age for adjustment of age, you can use a propensity score. So you can match on age, you can match on the propensity score. You can stratify, you can restrict to a particular range of the propensity score. You can do modeling adjustment, just put the propensity score into a regression model, and you can weight with the propensity score. And there's a range of weighting techniques such as IPTW or SMR weighting, and a few others that are being developed. And so those are the two steps: build it and then use it. Okay, so we're going to transfer it over to Jeremy, who's going to talk through a particular example, celecoxib.
Yeah, and so build it and then use it. That's going to be the theme of the next 3.5 hours. We'll show you how to think about it. I guess that's really step 0, John, right? How to think about it and then build it and then use it.
All the causal thinking.
Yeah, all the causal thinking. And so we'll do that with a lot of pictures and hypothetical examples, and some real world examples as well. And then we'll dive into the details of how do you build a propensity score. And that's kind of a multi-step process. How do you choose what goes in a propensity score? What do you leave aside? How do you actually do the estimation of that propensity score? And then we'll spend a substantial amount of time, probably after the break, on how you actually use that propensity score to achieve this goal that we're talking about, which is a balance between the treatment groups that leads us to a causal interpretation of the treatment effect. But we're gonna, as I said, use some hypothetical examples, because sometimes you can just draw a picture better than you can find in any real data. But we do want to have a couple of concrete examples as we go through. And one of those will be this question of the drug celecoxib. It's an old example, but it's really, I haven't found a better one. Celecoxib, Celebrex here in the United States, is an alternative to non-selective, non-steroidal anti-inflammatory drugs, non-steroidal NSAIDs, like ibuprofen or naproxen or other kinds of non-selective NSAIDs. And it's used because it has been shown to reduce the incidence of gastrointestinal bleeds and other adverse GI events. So, to the extent that ibuprofen and naproxen and such are hard on your stomach, not a technical phrase, but are hard on your stomach and can lead to bleeds or other kinds of adverse GI events, celecoxib is better in those ways, with presumably equivalent ability to reduce pain. And so, sorry, go back one second. We want to look fundamentally at this question of celecoxib versus non-selective NSAIDs for the outcome of GI bleed. And thinking about the outcome here, we've chosen this outcome of GI bleed. This is, in some ways, an effectiveness outcome. The drug is meant to reduce pain. So kind of true effectiveness of the drug is reduction of pain. But the raison d'etre of the medication, at least one of them, is that it is safer for GI bleed than the alternative. Certainly, there's been discussion of safety questions. I think celecoxib, 10, 15 years ago, there were questions around MI, and I think those all came out null. So we're not focusing on safety today, but looking at more of an effectiveness question. And the reason I draw that out is because effectiveness questions tend to be questions that are more confounded than safety questions, because drugs are chosen to be effective. And so all of these channels of confounding that John mentioned in the implicit, explicit, I'd say tend to be kind of more prevalent when we're talking about effectiveness questions on average than when we're talking about safety questions. So like many of these kinds of examples, we'll be looking at patients enrolled in a large national US database from a US drug insurer, or medical insurer rather. And on the next page, I want to get some feedback from the group here. Maybe we'll try this by chat. And again, this is new for us too. So pardon us if the mechanism doesn't work as intended here, but anybody have any answers to these questions that they want to put into the chat? What do people in the celecoxib group look like as compared to people in the non-selective NSAID group? Are they older, younger, taller, short, whatever kind of characteristics that we could measure? What do we think the celecoxib group would look like as compared to the non-selective NSAID group?
So we're getting some input from the chat: age, other comorbidities such as frailty.
Yeah, and to Jay, who said this is technically a safety analysis, I agree. But it's in the spirit, I would say, of an effectiveness analysis, since improved safety is one of the kind of reasons for the existence of the drug. So yes, in a sort of a technical sense, it's a safety analysis, but it has the sort of confounding patterns of more typically of an effectiveness analysis. So let's look at some of these answers here. And thank you all for your answers. And by the way, you all saw that the winner, at least as I tabulated it to our distance game, was Taipei. So Taipei, Seattle, actually not by as much as I would have thought. Geneva, 5,200 miles, Taipei, 6,000 miles. Actually, the second place was actually Barcelona, which I actually wouldn't have guessed either. And I'm sorry if kilometers is your metric of choice. This website happens to measure in miles, but okay. So older age. So let's see what age looks like. I actually wouldn't myself assume older age, but maybe in the sense that older people are more at risk of GI bleeds, and thus if you're looking to reduce risk of GI bleed, you might use that in a more broadly older age population. I don't know. Comorbidities, we'll have to look at that.
Yeah, and Jeremy, even if the risk of bleeding itself is not much different, the older person might be at higher risk of bad outcome from a given bleed.
Right. Yeah. Comorbidities as a whole, we'll take a look at that. More frailty, I think that's similar to the age question. And
anticoagulants is on the list now.
I was just going through in order. So probability, higher GI comorbidities, prior risk of bleeding. Yeah, that's a big one. So we will see that people in the celecoxib group probably have a much higher prevalence of history of GI bleed or other such comorbidities. Celecoxib group more at risk of GI bleeds, demographic differences. And then, as John was saying, the last one, anticoagulants. And you didn't say, Anthony, which way you think that's going to go, but I'm going to assume you're saying that more anticoagulants in the celecoxib group. You want to just, okay, yeah. So let's see if that is true.
Okay, you ready for the table?
So this is raw, unadjusted data. We have our treatment group here, which is celecoxib, 103,000 patients drawn from this database. We have about 10x that number in our referent group, which is diclofenac or ibuprofen, 1.82 million patients. And highlighted a couple of these. So the celecoxib users are, as predicted, older, so 12 years on median, older than diclofenac or ibuprofen. So good call for those who noticed age. Matthew, I'm going to come back to your point in a moment. There are slightly less female users of celecoxib, slightly less female, much higher history of osteoarthritis, so 25% versus 10%, much higher use of opioid analgesics, so other kinds of pain medications, 47% versus 31%, and higher use of corticosteroids, about 30% versus about 20%. As the course goes on, I'm going to start rounding more and more. And about a 2x difference in the use of statins, about 30% versus 15%. I think we have one more slide on this, right? You go to the next one, John. I think we have a second page of this, right? Oh, maybe we don't. I'm sorry.
Yeah.
No, sorry, go back. That's my bad.
Okay.
Anticoagulants, I should have highlighted also. That's the one I was looking for, and I just hadn't highlighted it. Anticoagulants, as predicted, 6% versus 1.5%. So, relatively low kind of total in both of those groups, but a 4x difference in the celecoxib group. So, what do you think? Do we say, great, we're going to use these data, crude analysis, that's going to get us exactly what we want, celecoxib, GI bleed? Or do we need to do something else before we start to analyze these data to get that causal interpretation? Who votes for use the data as is versus do something else? We could have done a polling question, John. We had all the technology available to us. So yeah, I think Manel speaks to the for the group saying do something else, and I totally agree. And thank you, Jay. And Matthew, I think the question about wealth and access, I think that's always something that we have to consider. Maybe something that's somewhat mitigating in this case is that the drug is, I believe, now generic. And thus, available at a much lower price point than it would have been when it was a branded medication. But absolutely access and ability to get a drug and those variables that are correlated with such ability are always important to consider. So thank you for bringing that up. So here's another way. Oh, there we go. Let's look at the next one. Another way of looking at the celecoxib data. We now have 103,464 patients, no rounding there, in the celecoxib group, and the same 103,464 patients in the diclofenac/ibuprofen group. They are now median 56 versus 57 years, so that giant difference, a 10-year difference went away, went down to like a 1-year difference. Osteoarthritis, 35%, 33%, much more similar than it was before. Opioids, 47% versus 48%. Anticoagulants, 5.9% versus 5.1%. Corticosteroids, you can see something kind of interesting happened here between the last slide and this slide. So first of all, we lost a whole bunch of diclofenac and ibuprofen patients. Remember, we had almost 2 million, and now we have 100,000. The second thing that happened is that we've gotten much better balance on all of our variables, and in particular on the ones I've highlighted. Now, we got balance, but what happened? Did we sort of get balance by moving the diclofenac group towards celecoxib or celecoxib towards diclofenac, or did we meet in the middle? What happened here? Anybody want to sort of qualitatively? Yeah, so matching happened, and exactly, so diclofenac to celecoxib. So what we did is we found celecoxib users, and then we dropped into our population of patients who used diclofenac or ibuprofen and selected out patients who looked a whole bunch like our celecoxib users. So we didn't meet in the middle here. We found a group of patients who were treated with diclofenac or ibuprofen who looked very similar to our celecoxib patients. And again, if you think back to a randomized trial, what would you do in a trial? You would find patients that are similar to one another, assign celecoxib, assign ibuprofen. And if someone was very, very different, they probably wouldn't be included in the trial because the exclusion criteria of the trial probably wouldn't have allowed that patient to be in, right? So what we're doing is setting up something, again, sort of akin to a randomized trial. And if, while we're talking about randomized trials, if I publish these data in the New England Journal of Medicine, and I didn't tell you whether this was randomized or observational or real world or anything like that, let's just say I said, trial of celecoxib versus diclofenac versus ibuprofen, would you believe that this was randomized trial data? Someone giving a yes or no? Nope. Anthony says nope. Why, Anthony? Can you type that fast? Sorry to make everyone type so fast. I mean, is it just like a little too imbalanced to look like a randomized trial? Like things are just a little off by a little too much? What if the header of this table was a randomized trial of celecoxib versus diclofenac or ibuprofen? Huge N. That's a very good point. Okay, so I'd have to blind the N. All right, I guess where I'm trying to lead the group and maybe not successfully. So good job for keeping me on my toes this morning. Is that this table looks like it came from an RCT, maybe, right? But we didn't get this by design like we would in a randomized trial where we flip a coin, A goes here, B goes there. We constructed this and we did a lot of work to do it. And what we're going to show you over the next couple hours is how that work got done. And the balance that we see is only among these measured covariates, or at least we only know that it's among these measured covariates. We may have gotten some balance some other ways, through things that are correlated to these measured covariates, but this is only guaranteed, if you will, among the measured covariates, and as such, no balance among the unmeasured covariates is implied. But analytically, we can treat this like an RCT. And we have this notion of equipoise or clinical equipoise, that the patient had kind of an equal shot of being treated with celecoxib or ibuprofen, like we would have in an RCT at baseline of this study. So maybe not, it doesn't look exactly like an RCT, but we're start to live in that world a little bit. But always remember that we arrived at this through construction, not design.
That's right. Equipoise is this, it's sort of an abstract concept, but this is, in effect, what Jeremy has done with that table 1 is empirically identify patients where the equipoise seems to be acting, where, because we found patients who have identical characteristics who were treated with different medications. So
the theory goes back to the 80s. All good things go back to the 80s. Rosenbaum and Rubin, many people have probably read or seen or heard of this paper. They use the propensity score to adjust for observed covariates in observational studies. We talked about how it's a conditional probability. We talked about how it's a probability and thus a number between 0 and 1 inclusive. And it's a one-dimensional summary of multi-dimensional covariates, meaning it's a summary score. We've collapsed a whole bunch of information about covariates into this single number. And if we look on the next slide, I think this is the one that has some Greek letters, yes. And we won't go through all of this, but you're basically saying that if you can construct independence between these two groups, then you can look at it as randomized within small subgroups of X, and you can get a causal notion out of it if we look at the next slide. I'm sorry, I'm like looking at two different slide decks right here. If you go back one, sorry, John, I should have caught that. The really important statement is the fourth bullet. It says, assume treatment selection independent of outcome given pre-treatment variables. So if Z is the treatment, you say the treatment is independent of the outcome given X, your covariates. Do we have another name for that statement? This is something that comes up a lot. Usually starts with the word assume or assuming. Assuming no.
Something we do in all observational research.
And I'll say it's a big assume, it's a big assumption. One that we tend to maybe kind of walk by a little bit sometimes, but it's a big assumption. That is the assumption of no unmeasured confounding. So propensity scores, like we said more informally a couple slides ago, don't make up for unmeasured confounding unless you happen to sort of make that up through association somehow. But propensity scores don't solve the unmeasured confounding problem. In fact, they rely, like many other techniques, on no unmeasured confounding. Does that make sense?
And this is an explicit representation of that, what we had mentioned before, of if there's a sufficiently strong and accurate causal model, this is that is saying there's no other variables that affect treatment selection.
All right, so let's, instead of looking at Greek letters, let's look at some pictures. If you match on this balancing score, you will see this effect that to this day, and I've been teaching this course with John for a very long time, that to this day seems like magic. If you match propensity score 0.43 in the celecoxib group to propensity score 0.43 in the ibuprofen group, and you do that again and again and again for all your different observed propensity scores, you will get that magical table like we saw that looked like it almost came from a randomized trial, just for having done the matching. And that always feels like magic. So let's look at how this works. This is the interactive part, or an interactive part. So get your typing fingers ready, okay? But I want to orient you to a picture that we're going to be using a bunch over the next couple slides. So this is distributions of propensity scores. And we will, and we'll apologize for this, we'll use treated and untreated sort of equivalently to drug A versus drug B, or treatment versus referent. The concept is that you have two and only two treatment choices, and the patient gets one or the other. And so whether you call that treated or untreated, or drug A or drug B, kind of structurally doesn't make a large difference, but you will see a little bit of a mix of terminology. So these are distributions of propensity score. So propensity score along the x-axis, we observe that the x-axis goes from 0 to 1, as promised. And on the y-axis, you have numbers of patients. So, for example, if we look at propensity score 0.35, call it, there's about 1,200 patients with such a score. Okay, I want to leave this up on the screen for a little bit, and I know this is going to feel a little bit like dead air time as people type, but can you look at this and digest it a little bit and tell me some things that you see about these distributions? So the pink line is the untreated or drug B group. The blue line is the treated or drug A group. What do you see about the numbers, about the ways that the two groups are distributed, about anything on this slide here? This is the part that feels awkward, but it's not. Everybody, just trust me, it's not awkward. Okay. So obviously, the treatment group has a higher propensity score. Yeah, that's a very good observation. So the average propensity score among the treated is higher than the average propensity score among the untreated. And that is no surprise, and that is no that's no mistake. People who are treated should have a higher probability of being treated. That's exactly what this propensity score is intended to reflect. So I think that's good. And no, the word didn't sound sour. It's just that's the way I pronounced it. So my bad. But trying to have a little fun with the chat here.
And it should be obvious, because it's exactly what the propensity score is doing. It's predicting treatment, and so the treated people should have a higher propensity score. But yeah, it's a good thing to check. It's an important diagnostic, and I use this kind of diagnostic in all the propensity score analyses I do.
So numerically, I'd say, just eyeballing it, right? The average treatment, the average propensity score among the treated is what, like 0.6, 0.65, something like that, right? and the average propensity score among the untreated is, again, just eyeballing it, like 0.35, maybe 0.4, and that's what I would expect. And remember, this is hypothetical data. We just drew this, and by we I mean John. Okay, and then Katu says more untreated people. Yeah, so there's a surplus, if you will, of untreated patients in this example, meaning that there are kind of propensity scores aside, there are just more untreated patients than treated patients, and maybe kind of a 3-to-1 ratio, roughly speaking.
Yeah, and often instead of having an absolute number of people on the y-axis, it will be some kind of kernel density function that's plotted.
Any other observations? And just a global apology if I mispronounce any names. I do apologize for that. Oh, this is a really good one. So thank you, Astrid. No treated patients with a 0 PS and no untreated patients with a 1 PS. Well,
it's a good segue.
Very good segue. And I will say somewhere between 0 and very few. It's hard to tell unless we like really blow up this plot. But Astrid makes a really good point about the tails of the distribution, is that because these are probabilities, you would expect certainly basically 0 treated patients with a propensity score of 0, right? If you have a 0% probability of being treated, at least in our model, and you get treated, that seems strange. If you have 100% probability of not being treated, 100% probability of being treated, and yet you're not treated. Did I get that right, John? That would also be strange. Astrid, the observation you make about the tails of this distribution is very important, and we will come back to that, perhaps even on the next slide. John, am I wrong?
Okay.
Yes, look, there we go. It's right on the next slide. John, you want to take over here?
Sure. Yeah. So, I mean, there's this idea, and I think this is what's called the positivity assumption, that when you have your analytic sample, you want to make sure that at every level of the propensity score, there's a non-zero probability of treatment. And so if there's an area of your propensity score distribution, is an important reason to look at these distributions as a diagnostic. If there's an area where there are people who are treated or untreated in any range of the propensity score, but nobody in the comparison group, that area you probably want to exclude, because it's basically violating that positivity assumption that there's a non-zero probability of either treatment in that particular range of the propensity score. But there's other reasons, and so the focus in this slide is about the high end of the propensity score between 0.95 and 1, so 95% to 100% probability of receiving treatment, but you don't receive treatment. So the people who are untreated in that range, or at the low end, the 0 to 5% probability of treatment, very low probability of treatment, but they actually receive treatment. If we were to blow this up, as Jeremy says, so that you can actually see it's not quite 0, it may be very close, but the idea is that what does it mean to have a very high probability of treatment and actually not receive treatment? So these are like the ideal candidates for a medication, but for some reason they get the alternative. They either get no treatment or they get treatment B. Any thoughts about that? People at the high end, almost certain to get treatment, but they in reality don't get treatment.
Yeah, so let's pause and think about this. And as you're thinking about this, I'll share a meta intuition, which is that propensity scores are very intuitive. And the reason that we spend a lot of time at the upfront looking at hypothetical distributions and stuff is to help everyone here sort of develop that intuition about what propensity scores are telling us. So if we see someone has a 0 probability of treatment and they're treated, what does your intuition tell you? What could be going on? So again, we'll take one of those potentially awkward feeling pauses as people type, but we actually know that it's not really awkward. It's just part of virtual online learning. And it's just an opportunity to have a sip of coffee. I'll demonstrate with my large Dunkin' Donuts iced coffee. Excellent coffee. Anybody have any thoughts that they want to share in the chat?
Yeah, so there's a good one. Unobserved covariates.
Great ones, yeah.
Propensity score missed something. Patient refuses treatment. Yeah, these are all good thoughts. Yeah, so you could be the ideal candidate for treatment A, and you just refuse it for one reason or another. You may have known somebody who took it and had a bad reaction, and you're just not going to take it because of that. There's a whole range of things that may not be captured in the database, but that actually influence treatment and lead to sort of unexpected treatment decisions. And an important one is also, maybe the propensity score missed something. For example, you could have a contraindication, even though otherwise you look like the ideal candidate, but you have a contraindication to the treatment. And that variable, the contraindication, is actually not part of the propensity score. And so that the propensity score misses the contraindication, and it looks like you have a really high propensity score, and you just but you don't. And so that's good medicine, but it's also, it shows the limitations of the data source.
Yosef, you bring up unobservable covariates. And I think that's a really interesting one. And so sometimes we have unmeasured confounders, and sometimes we have unmeasurable confounders. In the end, kind of ends up in the same boat, which is that we need to have measured something that we didn't measure. But sometimes if something is unobserved versus unobservable, maybe we can do something to kind of push it forward and observe it. But that's a really good point. And Georgi, you mentioned off-label treatment. John, I was reading the chat. You didn't mention off-label treatment yet, did you?
No, I haven't. I was just about to, so go ahead.
Oh no, you go ahead. It's a good one.
Yeah, because off-label treatment, this is great. The propensity score, as a summary of all of these covariates that went into treatment selection, what it does is it's implicitly it's identifying different phenotypes. So different phenotypes of patient characteristics, and as I say, at the very high end, these are a phenotype that is kind of the ideal candidate for treatment, and at the low end is the marginal candidate for treatment. But sometimes it's empirically based, so it's based on the data from whatever analytic data set you have. And what can happen though is off-label use. An off-label use is when a person receives a medication for something that's not part of the label, and so medications have a range of effects, and a smart clinician can think through the underlying disease process and say, this medication, even though its intended indication is X, we might use it for this condition Y, thinking through the underlying biology and saying this probably will have a beneficial effect in the patient, and so then they'll use it. But that patient will look very different than the typical phenotype of patient who gets the drug. And so the patient who receives the off-label use would have an empirically very low propensity score, but they get the treatment. And so that's a really nice example of when you see treatment against expectation.
Yeah, and Anthony, sorry, you said exactly what I was thinking, that's related to, but I think an important call out as a distinction from Yosef's comment, which is it could just be that you've missed something. And so it's not that it's unmeasurable, it's just that maybe it's even measured, but it didn't make it into your propensity score. There's something important about this treatment choice mechanism that isn't included in the model. And so our model is modeling something that isn't kind of the true process, or at least isn't as close as it could be to the true process. And so, Anthony, I would summarize your item here as, whoops, we missed something. And that's a definite possibility.
Yeah.
Okay, I was looking, let me read this question. If you restrict your original cohort to people with the diagnosis for the indication of the drugs of interest, do you overcome this issue of off-label use? I mean, maybe, possibly, but as a mentor of mine told me when I started in this field, in the real world, everything happens. And so you will, Matthew, probably get closer than if you were less restrictive. But I wouldn't expect that you're ever going to sort of reach perfection in this, because everything that could happen, will happen, especially when we're talking about data sets that include, close to 2 million patients, like the celecoxib example. There will be a little bit of everything. That's just sort of the law of large numbers in some way. And also, again, this isn't propensity scores, but just kind of epi in general. As you restrict your original cohort, you might be getting a sort of a more and more focused view on a group of patients, but you may lose the ability at that point to zoom out and generalize your observation that you make in the end to a larger group. So, I think it's always very much about whom are you trying to understand and whom are you trying to generalize the result to as you make those choices of limiting or expanding your treatment group. And Eng asked the question, or Cheryl, would you exclude all patients with a contraindication to drug A or drug B rather than using contraindication as a covariate in the propensity score? That's a good question. I probably would. What would you do, John?
Yeah, well, it certainly addresses a lot of the issue around treatment against expectation for contraindication, but a lot of times contraindications are not absolute. There's kind of relative contraindications, in that physicians may try a medication in a patient even if they do have a contraindication, as long as it's not really dangerous situation. Okay, so I think we're done with the chat. Is there anything else we want to touch on there?
No, so let's look at our answers and see if we covered all of them in the chat here. So patient is treated, but had a low propensity score, meaning we predicted that they wouldn't be treated, and yet they were. That patient could be different in some way. Off-label use. Do we cover
the last resort?
That's a good one.
Yeah, so if you've tried, or the clinician, your prescriber has tried everything and nothing has worked for you, they may go to something that may have very little chance of working, but there's no other option. So that maybe tried as this last resort. And what that will show up as is the very atypical patient will receive the medication. It's very much like off-label use, but it's a particular form of off-label use.
Patient treated in error is a good one. There's just mistakes. In the real world, everything will happen. Sometimes there'll be mistakes.
Yeah, this is the treatment in error. Often you don't want those patients in your analysis if you're doing the typical. I want to compare celecoxib to naproxen or non-selective NSAIDs, but sometimes you're particularly interested in those errors. If you're interested in finding, either maybe a situation where there's an opportunity for education, or maybe it's from a regulatory perspective, they could enhance the label warning to try to affect therapy, or identify potential name recognition errors that can happen. And so this would be one place they would show up, is if somewhere along that prescribing process of the prescriber's mind to the patient actually receiving the medication, somebody made a mistake and pulled the wrong thing off the shelf, or the prescriber wrote the wrong medication down, just because they mix it up with another name that was very close. This could show up in this way.
And then characteristic not captured in the propensity score determined treatment. That's the one we talked about where we didn't measure something that we should have. And I believe we have talked about the rest of these. Patient refuses treatment was brought up by, I'm looking back in the chat, by Jocelyn a few minutes ago. So thanks, Jocelyn, for capturing that.
All right. So we've
All right.
addressed some of these things. The next, the hypothetical distribution that we've been showing you and focusing on the tails more recently, but it's just one of many possible distributions that you may see. And what we're showing here are some other sort of distributions. And we wanted to talk about what would you do if you developed a propensity score and thought through your causal contrast that you want to make, and you end up, after building your propensity score, looking at this first, what I consider an important diagnostic, and then you run into a situation like distribution A, where there's not very much overlap between the people who get the drug and the people who are in the comparison group, either untreated or treated with a different drug. What would you do with a situation like A? Any input on this?
And what's your intuition about what's going on in a situation like A? John, maybe we should change the title of this course to Propensity Scores More Than Just Confounding Adjustment. Really about prescribing intuition, no? Or
it's the camel's nose under the tent to talk about general epidemiology ideas. Okay.
Yeah.
That's a great answer.
A clear guideline.
Yeah. So if for example, there's a kind of a clinical practice guideline that almost deterministically separates people who get treatment A from people who get treatment B. The guideline says if you have this condition, you should get A. If you have these other conditions, you get treatment B. And the prescribers follow those guidelines, then you'll often end up in a situation like A, where the characteristics of people who receive treatment are very different than the characteristics of people who are in the comparison group, either don't receive or receive the other treatment. And that's not a bad thing. It's just the function of the practice guideline on practice. But from a research point of view, this is a big problem. That is, it's a red flag. If you see a situation like the distribution of propensity scores in scenario A, you should stop for a moment and think about, do you really want to proceed with your study the way you had originally planned it? Because there's something very different about people who get treatment A and the people who get treatment B. Or it's just that there's essentially no overlap, and that if you do any of the propensity score analyses, you'll be sort of restricted to the area of overlap, the area of common support on the propensity score distributions, and that little triangle of patients sort of around the 0.5 or a little bit less than 0.5, that's all of your inference will come from those patients. And the question you need to ask yourself is, do you want all of your inference to come from those patients? Any other thoughts, Jeremy, about that?
Yeah. So, Katu, Thibault, a ton of and again, if I've mispronounced your name, I apologize, and feel free to direct message me and give me a pronunciation guide so I don't continue to mess it up. But
at least you're trying.
You're all thinking sort of in the same domain here, which is that this is like two different groups, and it's sort of unclear why we were comparing them. And again, I think it always goes. It often helps to go back to the randomized trial paradigm, and this is very much in line with Miguel Hernan's target trial principle, which I think is a recommended read, certainly. If this were a trial, would you end up with overlap like that? It just looks like we selected two groups of patients that are very, very different. So maybe here we're looking at not celecoxib versus ibuprofen, but celecoxib versus an opioid, or celecoxib versus something that isn't really an alternative treatment choice for that medication. Opioid is probably closer to B, so I take that back. But
yeah, but in its original formulation, the concept of confounding by indication is basically the scenario A, because what that is saying is that a group of patients have the indication, and you're comparing to patients who don't have the indication. And it's a really essentially intractable kind of confounding situation where you can't overcome it because you have a group of patients who are just very different than the comparison.
What about C? Let's go the other extreme. And actually, let's make it even more extreme. Imagine that the blue and the red lines are pretty much right on top of each other. What's your intuition about case C? Yeah, so Cersei says no preference really. Yeah, these are the same drug, or I mean, not same drug, but the same indication. And maybe it's, remember, in the celecoxib example, I said celecoxib versus diclofenac or ibuprofen. C could be the diclofenac versus ibuprofen contrast. Very similar drugs, same class, same indication. There seems to be little preference between the two. Generic and brand. That's a good example. Now, Pooja, you say too much overlap, similar issues with not being able to draw inference. Let's think about that. So, John, what do you think there?
Well, I mean, if there's very little treatment selection, if you have a situation like C, then you can actually draw the inference without even doing an adjustment. In the most extreme case when they completely overlap, and even when they're off by a little bit, or the other sort of happy way to think about it is that you're not going to be asking the propensity score to do very much for you in terms of confounder control, and so that gives you a lot of assurance that whatever result you have at the end is likely unconfounded. So that's I think when I say happy, it means as a researcher you have more confidence in a situation like that. But I want to say you could either end up in situation A or situation C. This is assuming what we've talked about so far assumes those are correctly specified and modeled propensity scores, but there is a set of circumstances where you could end up with a distribution like A or a distribution like C that you arrived at by error, and that's probably what we should talk a little bit about, because I've seen both situation A and situation C that are based on error, and those are really important instructive topics.
So C is the case where you have drugs that essentially there isn't really a treatment selection going on. You could choose randomly and it would be okay clinically. You'd be in equipoise by just saying either one of those is fine. And there isn't kind of a strong driver of preference one way or the other. So I'd say brand and generic could be a pretty extreme example of that. That's the same medication. And whether someone gets, branded Lipitor or generic atorvastatin, you're not going to see most likely, a large difference in patient characteristics. Maybe a slightly less extreme version of that is two different SGLT2 medications for diabetes, or two different DPP4 medications. So choosing medications within the same class, if the choice of medication is essentially equivalent clinically, you may end up in a situation like C. And in some ways, it's super easy at that point because you don't really have to do much. There's not much confounding. If you just compared those two drugs, especially if those curves were right on top of each other, and you had specified the propensity score correctly, which means that there really is no difference. That's easy street, epidemiology wise. But to Pooja's point, you may also not be looking at a very interesting question potentially, because you may have just no reason to make that comparison, or you could be looking to prove that there is no difference. So if you're looking at the brand versus generic question, maybe your treatment, your research question is there a difference in effectiveness? Is there a difference in safety between branded and generic Lipitor? So you could have, no treatment selection, but and maybe no expectation of difference, but that could be the thing you're looking to study. So does that make sense? And Tanavi, does that make sense to you as well?
All right, but you could end up in a, okay, yeah, so still.
Yeah, and Thibaut, should we worry about having too little information available? Only if we didn't measure something we needed to measure, and that's why we have such great overlap. So if we have great overlap because we didn't measure that one thing that makes someone get drug A versus drug B, and that's why it looks like we have perfect overlap, then yeah, we should worry about having too little information available. Otherwise, if you assume you get everything, and that was, in the Greek letter slide, we assume that it is independent of covariates, meaning no unmeasured confounding. A strong assumption, no doubt, but if you make that assumption, then you have the right amount of information by definition almost.
But these figures have to be interpreted with external knowledge. So you have to use what you know about how treatment A is selected relative to treatment B. And if clinically you expect very little difference in that treatment selection, and you end up with a situation like A, when you think you really should end up with a situation like C, that should be a warning to you that you probably are missing in your data set an important variable, or you have it in your data set, you just include it in your propensity score, the variable that really was the characteristic that prescribers use to select treatment A and treatment B. So
is B best? I would say without a doubt, A is worst. B is sort of your Goldilocks case, sort of just the right amount. But C isn't bad necessarily, right? C could be just fine for what you're trying to do. But C makes me suspicious unless I have, like Tanavi was saying, that external knowledge that says, yeah, of course these should be similar because it's the same class of drug or it's branded versus generic. But B's the, I'd say, most interesting area probably on average to be operating in. And if you have A, something's going wrong. And is this a good time to talk about instruments, John?
Yeah, absolutely. So, I mean, the other thing
John's got a story, everybody. John's got a story about scenario A. So let's sit back and listen to John's story because it's a good one.
Yeah. So, and this goes, ties in with using external knowledge to help inform your interpretation of this diagnostic tool of the propensity score. And so if you have a situation like A, what that's saying is that these two groups are very different, and there's just that the combination of characteristics that went into the propensity score, creates very different groups. What the problem that can lead to A sometimes is that you included a variable in your propensity score that's very strongly associated with exposure, but it may not be a confounder. So it's not a predictor of the outcome, not a prognostic characteristic of the outcome. And so you actually didn't need to include it in your propensity score. And doing so harms your efficiency because it creates this situation, whereas it should be a B or a C. But that one variable, whatever it is, led to greater separation than you would normally have. And the example that I have, and this is real world. I learned from my mistakes, and I want to use those mistakes to help all of you not repeat them. So the idea was I was trying to compare two anti-tumor necrosis factor drugs, two anti-TNF drugs used for rheumatoid arthritis, infliximab and etanercept, and so in my thinking, before I even built the propensity score, I was expecting a situation like C. These are drugs that have very similar indications, very little expected difference between people who get etanercept and people who get infliximab. And I ran the propensity score, and I built the propensity score, and I ended up with a situation like A. The propensity score had essentially no overlap. The distributions had essentially no overlap, and I was wondering, how could that be? These drugs are largely used for the same kinds of patients, and then I what I had done. I need to give you some more background on how I built that propensity score. Is I had talked to clinicians. I had put together a list of variables that I wanted to include and gone back and forth in the study protocol. And we had that list of a priori specified variables. And there were also some variables that we included in the propensity score based on empirical consideration. So we figured out in the data set what is correlated with receiving infliximab relative to etanercept, and we added those variables to the propensity score. Largely that's an important, I think, an important sort of safety net that allows you to find variables that you didn't have the smarts to think about in advance, but it created situation A because what it was including, the variable that it had picked up was placement of an IV line. So there's a CPT procedure code for placing an IV line. And for those of you who don't know, infliximab is given by IV infusion, and etanercept is a subcutaneous injection. So that if you get infliximab, you need to have this IV line placed, and so that it was a very strong correlate of exposure, but having the IV line placed wasn't a predictor of the outcomes they were looking for. It was cancer or infection. And so that once we discovered that variable was part of the propensity score, we just removed it from the propensity score because it was a problematic variable, and then the distributions moved more to C. So that kind of example, though, is an important component of variable selection in your propensity score. You only want to include confounders and not correlates of exposure that are not related to your outcome.
Yeah. And Tommy, I'm going to digest what you say here, but I want to let everybody know that there is a slide 34, and we will get there. In fact, we will do that right now because I didn't want everyone to think that this was the last slide we were ever going to see this morning. Now, we spend a long time on that because the intuition is critical. And really, once you get the intuition, everything else, I think, in my experience, snaps into place. But this is sort of the turning point in the discussion where we go from sort of the intuitive and the theoretical into, okay, now how do we do it? How does it work? And so let's make sure that sort of the intuition questions are all answered before we move on. So Tommy says, my understanding is C, actually, John, let's go back one slide, shows a likelihood of indifferent baseline characteristics after using the propensity score that added A or B. I'm not sure I follow. John, do you want to take a stab at this?
Yeah, I mean, if your population is pretty homogeneous, I mean, that's not necessarily a bad thing. As you're saying, if the selection of patients into treatment A and treatment B are largely driven by sort of small differences or almost random selection, that's not a bad thing, because then it allows you to compare those two treatments without a lot of adjustment. And so, but you could end up with a situation where you're answering a very narrow question because you have this highly selected homogeneous population that may not be very generalizable. And so you always want to consider the trade-offs between the validity of your comparison and then the generalizability.
Okay, so last chance, which is not really a last chance because you can always ask, but last chance while this slide 33 is up to ask any questions about intuition about propensity scores. Okay, type away if you have any. Otherwise, we'll move on a little bit. How do you get a propensity score? So we said way back when, John, that there were two steps of doing a propensity score analysis. The first one was to build your propensity score, and the first step, and the second step was to, what was it? Oh, right, use your propensity score. How do you build that propensity score? Where does it come from? So we've sort of assumed the existence of a propensity score to date. Now let's talk about how you actually get it. So a propensity score is a predicted probability of treatment based on measured covariates. Remember, it's a number between 0 and 1, and that number is a probability. And we have in our toolkit a number of statistical models that we can use to predict probabilities. In fact, we have one that we use probably almost every day, and that is logistic regression. And so here we're using logistic regression as a predictive model, where we're not looking so much at the betas and trying to interpret the betas in any way, but rather using the predictions that come out of the model. Really, logistic regression is, I'd say, the most common choice. It may not be necessarily, always the best choice, and it's certainly not the only choice. We can use anything that gets us from here to there. And I define here as starting with some data, and there as having a predicted probability of treatment for each patient. And so we make the assumption that all variables predictive of treatment and outcome are included. That's our no unmeasured confounding assumption. That's a big one. But maybe a little more subtly, that the model that we're using, that the functional form is correct. So, maybe there are, very complex interaction terms that we need to be thinking about. Maybe there are, very strong non-linearities or non-log linearities that we need to be thinking about. In my practical experience, those things tend not to happen, but, we should always think about those possibilities. We'll come back to that later, but if you wanted to sort of put me on the spot, say, how do you estimate a propensity score? You have one choice, what would you do? I would say logistic regression. Okay, so now really nuts and bolts, what does that look like on slide 35? If we're working in SAS and we want to predict a propensity score, we say proc logistic, we add the descending keyword because SAS, and you say model treatment. So it's not outcome. Oftentimes when we're using SAS, we put outcome on the left there, but here it's treatment equals, some function of age, sex, history of MI, history of statin use, ... all the confounders that matter. And then that next statement, out equals PS model, that gives you a table called PS model, pred equals PS. My predicted value from this model is going to end up in a column called PS. That's how I get a propensity score. And so you get a table PS model that has the patient ID and the treatment, everything that's white shaded background, that's input data. The yellow is our prediction output. So we give it a patient ID, we give it, was the patient treated, what age was the patient, what sex was the patient, does the patient have a history of MI, did they use a statin? And you get a propensity score from that.
This is what I call the
talk we did about intuition, 20 minutes or whatever on that slide, right?
Yeah, this is what I call the trivial part of the propensity score is actually generating it. The hard part is all the thinking of what variables to put in and making sure you've got that right. And then the second hard part is at the end using it. But this building it is really trivial once you've done all the setup. And
okay, but if it's too easy for you, if it's too easy, we can use R. So on the next page, I'll show you how to do it in R. Just a little more complicated for those who like a slight challenge to their propensity score building. You would essentially run the same model in R. You say your model M is GLM. GLM is a treatment as a function of age, sex, MI history, statin. Family equals binomial. That gets you the logistic regression. You get a model back. You take that model and you predict values. You put that in the pred variable. But remember that the predicted values from a logistic regression are logits. So you have to remember to do the XBit, the inverse of the logit, to get the probability back. And so that last line there is the XBit. So the e to the prediction over 1 plus e to the prediction gives you a probability, and lo and behold, the resulting table is exactly the same. Now, probably the same for the first couple digits, and at some point, there's going to be some difference between R and SAS because they fit the models very slightly differently. But that's just kind of immaterial, really.
In the chat, somebody's asking about a stated example. We don't have a slide for a stated example. Maybe that's for next year, Jeremy.
Yeah, but it's very similar. Oh gosh, I haven't used data in a very long time, but it's the same idea. You run a logistic regression model, and then you use the prediction function to get a predicted value out of that model. And I remember it being just a couple lines of code. And so with this model, all eligible study subjects are assigned a score. And we talked about these assumptions here. We said there was more on all of this later, and that remains true. We're repeating ourselves a little bit. With missing variables, okay, that's a good one.
I think it's maybe missing values. So if a person is, has a missing sex or missing age or missing covariate of one kind or another, the logistic will not give that person a predicted value, and that's an important thing to think about. It's you'll end up checking your sample size, and you realize that not all people contributed to the propensity score estimation, so therefore not everybody gets a propensity score. And there are a range of ways of dealing with that. You can impute, you do multiple imputation or other forms of imputation for the missing variables, or you can accept the exclusion of those patients, but you have to somehow deal with that.
Okay, so we said 2 steps: build a propensity score, use a propensity score. And when you build a propensity score, we said there's really kind of any number of ways to do that. The most common, like by far, 99.9% of papers would use a logistic regression model to get a propensity score. But hey, you can use a neural network, you can use a tree model. If you use a tree model and you're worried about this functional form, tree models essentially capture all interaction terms implicitly, and so that's a different way of dealing with interactions. But again, sort of building a propensity score, if you give me one choice, easy, logistic regression. Using the propensity score, now that's where there's a whole lot more variability. Sort of matching is the easy case. So I'm going to give you a put it all together example where we build and then we use, and I'm going to use the propensity score with matching, but we're also going to spend plenty of time showing different ways of doing this. So just to set some expectations here, if I'm looking forward a little bit, I'm going to walk through this one example here, and then we will take our break so that everybody can get up and stretch a little bit and get some coffee or wine or whatever the time appropriate beverage of choice would be. I always recommend water. Water is really just good for any time of day, hot or cold. Okay, so you remember table 1, and we saw this a while ago. Celecoxib, diclofenac, or ibuprofen are treated and are referent, are drug A, are drug B. And there was a strong difference between these groups with respect to age and osteoarthritis and opioid analgesics and anticoagulants and corticosteroids and statins and all that kind of stuff, right? This was the problem. And you remember where we ended up. But now I'm going to put a few slides in between and show you how we got from the starting point to that ending point of that beautifully matched cohort with about 100,000 patients in each group, and really good balance on these covariates. So the magic, magician never tells their tricks, but hey, I'm going to tell you the tricks here. We start with patient characteristics as measured. So age, we'll code gender as female, sex, history of GI bleed, warfarin use, osteoarthritis, whatever those patient characteristics are that we feel are important, and those would be the vector of confounders. We do logistic regression, where treatment is modeled as a function of age and the female variable and the GI bleed variable and the warfarin variable and the osteoarthritis variable. We get a model from that where the betas say, for every year in age, our odds of being treated goes up by 4%. Females have 9% less probability of being treated than males. You can interpret these betas if you wish. You'll probably see some big numbers around things like warfarin and osteoarthritis that are strong predictors of whether a patient gets celecoxib versus ibuprofen or diclofenac. But again, we're not here to interpret those betas, but if you look at them, they should hopefully have some sort of kind of intuition behind them, maybe counter intuition. There's sometimes where there's some sort of weird counter intuitions. We can talk about that, but they do map to real world processes. And so they should be explainable in some way. But in the end, the thing we care about is that thing way over on the right, which is patient 1, their propensity score is 0.92. Patient 2, their propensity score is 0.17. Patient 3, their propensity score is 0.22, and so on and so forth for the next approximately 2 million patients in our data set. So we built our propensity score. Now let's use it. So one way of using it is matching. One way of matching is to randomly select a patient from our treated group. And we pick our first patient out of the treated group. We say that patient, we observe that patient has a propensity score of 0.67. We reach into our referent group and we search for the referent patient with propensity score as close as possible to 0.67. And maybe we find someone who has exactly the same propensity score. That's very, very unlikely because they would have to have exactly the same vector of covariates, and that just tends not to happen. But maybe they have a propensity score that's just a tiny bit different. And we make the match and we repeat. Now, what if we didn't find someone with a propensity score that was similar enough? And I haven't told you what enough is, but maybe within 1% or 2%, that patient doesn't get included. We drop that patient. But hey, we've got 100,000 treated patients and almost 2 million untreated patients. We're probably going to find matches for most everybody. So we find someone who looks similar, we make the match, we repeat. And I think on the next slide, we repeat again even, right? And repeat and repeat and repeat and repeat. And when you're all done, John, can you actually go back one slide? Look at the blue line. Look at the shape of the blue line. Look at the shape of the red line, right? There was overlap between these two groups, but there wasn't perfect overlap, right? This is a B situation, not an A or not a C. So we expect that most of our treated patients will get selected, some may not, but in the end, the shape of this curve is gonna look like the shape of the blue curve that we started with. Because remember how I said I did my matching. I take a treated patient and I find a referent patient who looks just like it. So what I'm doing is I'm building a total population where my treated drives the characteristics and my reference are chosen to match. So when we get to the end, we have this distribution where now it looks like C, by the way, because they're right on top of each other. That's exactly what we said we wanted. These are now kind of exchangeable. That's a big word, but I'll use it here. One versus the other, we're there. And if we look at the table, which I believe is on the next slide. Well, okay. This is hypothetical data. Sorry, I forgot the progression here. This is the real data. So you have a large number of untreated patients, right? Or the referent patients, there's 2 million, and a smaller number of treated patients. And you see that the whole distribution isn't sort of nicely covering the entire range like it was in our hypothetical examples. Does anybody have an intuition why the average propensity score in this population is about 0.05? That's my guess. If I were to look at everybody together, treated and untreated, and say, what's the average propensity score? I think I would come up with something right around 0.05. Someone have an intuition as to why that's true? Elizabeth, not quite, not quite. This is even before matching. I'd say my average propensity score in this population is 0.05. The mean of the probability, exactly. And what's the mean of the probability of exposure?
Right. Where does that come from?
Yeah, what is, we have another name for that. And again, this is all ties back to the intuition. Remember, I had about what was it, 100,000 treated patients and about 1.9 million untreated patients. So about 100,000 out of 2 million patients were treated, and that's about 5% if I'm doing my math right. And so my average propensity score should be exactly as Jun King says, the exposure prevalence of about 5%. So that's exactly it. So there's a lot of intuition all the way around here.
That's the maximum likelihood estimator of the propensity score. If you don't know anything else, you take the prevalence of your exposure, and that's the propensity score each person has. But we can do better than that using all the covariates.
And so as we split it out, you see that, like in the hypothetical examples, there's more untreated patients on the left and more treated patients on the right, but there is really nice overlap, right? And now just sort of take a close look, and I'm using the pencil not on the screen, but near the screen. I don't recommend using a pencil on the screen, but sort of tracing that shape where the green line and the green zone and the blue zone overlap, and just sort of imagine what that shape looks like. That's our overlap zone. So remember, this is pre-matching distribution. Post-matching distribution, you can't see the difference between the green and the blue because they're right on top of each other, like we said they would be, right? And what is that shape? That shape looks a lot like the shape that I traced out. Now it's a little taller now because we changed the scale a little bit, but it's that shape, right? So does this all make sense? Gosh, if this were a classroom, I'd hope that everybody would be nodding and saying this makes sense. But can somebody just tell me that this makes sense, just so I know that it's that human-to-human connectivity that we all look for. Makes sense. Thank you, Elizabeth.
Yeah, it makes sense to me.
Great. Does the intersection signify anything? Wondering if the propensity score associated with the intersection is used as a referent when comparing or understanding a patient's propensity score. Does the intersection? So the intersection is the area where you have overlap, and we define that kind of linking back to intuition as the place where there's equipoise between the two treatments, meaning that patient comes in and based on everything you know about them, either of the two treatments would be a reasonable treatment choice for them. One might be more probable than the other, but they're both reasonable choices. And so the intuition around that intersection is that area where there is equipoise between the treatments. Now, the propensity score itself, right, whether it's 0.5 or 0.1 or 0.25 or 0.5, like that itself doesn't really matter because, as we showed with the average of these propensity scores in this population being 5%, right, 0.05, that's driven by the data, and that's driven by the relative prevalence of the exposure versus the reference. So the score itself, I'd say, is not terribly interpretable. And in fact, I would very much caution against any kind of sort of external interpretation of the score, or trying to generalize the score outside the population, because it's very much tuned to this particular data set and this particular question. And Pooja says, no problem, sorry. Pooja says, can you match starting with the referent? You could, certainly. That is another way to match. And I don't know that it would necessarily give you something different in the end. You match starting with the treatment, and you will tend, in this example, to find a referent patient because there are just so many more of them. If you match starting with a referent patient, you would, for a large number of your referent patients, find no treated patient, and that referent patient would be dropped. And so in the end, you probably end up with a group of patients that's pretty similar to what would happen if you started with a treated patient. But I'd say convention, if nothing else, has us generally start the matching process with our treated patients. in Pooja, the smaller group is the rate limiting factor, and in this example, it's the treated patients. But in most cases that we have, I don't have a great reason for why this is. We tend to have larger reference groups than treated groups. I'd say that's just kind of a function of the kind of research we tend to do. Okay, so now we got to the slide that I think we were going to have like 4 slides ago.
The table.
Yes, the table. After all that talk, the table. So we showed you the 2 tables way back at the beginning. Now we showed you kind of the intervening process, some hypothetical distributions, some real distributions, and you can see that this is not actually magic. I'm sorry, but that this was actually a pretty straightforward analytic process to get from that sort of messy imbalance table to this really nice, pretty balanced table between the 2 groups. And I'm looking here because I just want to make John switch slides here, but we started with 103,464 celecoxib patients and 1,827,422 diclofenac or ibuprofen patients. So 2 things are interesting to me about that. Maybe there are more things that are interesting to you. One is that we were able to find a referent match for each and every one of our celecoxib patients. So we lost 0 treated patients, which is pretty spectacular. But we also, at the same time, lost 1.7 million referent patients. I don't know how that sits with you, but you know, another mentor of mine, a biostatistician, used to say, and probably still says, data are precious. And we just threw away a lot of data. And I don't know how that makes you feel, but we can talk about sort of the pluses and minuses of having thrown away a lot of data. But I just want to be honest and say we threw away a lot of data in that case. And some of that data we probably needed to throw away, right? Or throw away is a bad word, but needed to not use in our analysis because it wasn't part of the overlap. That isn't a place where the patient was truly in equipoise between the 2 treatments, but there was probably more referent patients that we could have selected than the ones we did, and maybe we should have done some more work to get more of those patients into the analysis. And guess what? We have some ways of doing that. And guess what? We'll talk about that after the break.
Somebody in the chat has mentioned 1 to 2 or 1 to 3 matching. Yep.
Yes, absolutely. Now the question is, Katu, do you require that everybody have 1 to 2? Do you require that everybody have 1 to 3? And once you start requiring that everybody have, say, 1 to 3 matches, what happens if you lose treated patients who you could find 1 referent match or 2 referent matches, but not 3? So then we got to deal with that situation. And maybe you say, okay, you can match up to 3 or up to 4 or up to 5. Great, we can do that too. Then we have some analytic issues that we need to deal with. It's sort of more irritating than anything. It doesn't really kind of harm the analysis in any way, but it makes the analysis just a little more complicated. And we could talk about that as well. So John, should we take a break?
Yeah, we'll take a break. Just one last point is that with 100,000 celecoxib patients, 1-to-1 matching should be fine for almost any outcome that you're looking for. But for situations where your treated group is much smaller and and that if you just do 1-to-1 matching, you may not have adequate statistical power for the outcome. That's the kind of situation where I might consider doing 1 to 2 or 1 to 3 matching, and with the considerations that Jeremy talked about, of whether you try to force everyone to have 1, 2, or 3 matches, or you just take as many matches as are available.
So after the break, we will talk about some of the various ways you can use the propensity score. And we showed 1, but we promised 5. So we'll show you 4 more. And we'll also give some more examples beyond the celecoxib example, and we'll have plenty of time to talk through a number of subjects. So let's take a 11-minute break. So let's come back at 5 minutes past the hour of your local time. If you're in India, maybe it's 35 past, I think that's right. But let's come back in 10 to 11 minutes, and we will continue on with our discussion. And thank you all for your attention so far. And really, thank you very much for your participation in the chat. It's great for me and John to have that connection with you guys. So thank you for indulging us on that. So talk to you in 10.
All right, thanks.
And John, I think if you stop sharing, Amy has a break slide she can share. Hello, everyone. We will begin to gather once again. Give everyone a moment to grab that last sip of coffee or give the dog one last treat, right, Amy?
That's what I was doing, so yes.
I had a question that came in, which Amy, maybe you can answer, is whose dog was that?
Unsure. Just a nice person's dog that let us use a free image from online.
John, I think you should switch. Yeah. I always forget where the little flip is, but to flip into slideshow view instead of presenter view. Maybe it's Zoom and you have to share the alternate screen or something. So while John is working with PowerPoint, there we go. Any questions that people want to jump in with in the chat here or through any other mechanism? Okay. Well, while John is getting that set up, let's talk a little bit about part 2. As I said, we're going to focus on different ways to use a propensity score, and in particular, hey John, that looks great. And in particular, 5 different methods of using that propensity score. So we talked about matching. We'll talk about restriction, stratification. Oh, that was great, John. I wouldn't change it. Weighting and modeling directly.
All right. And you're seeing the full screen then?
No, can you go back into presenter view or into slideshow? Yeah.
There we go.
Hasn't come through for me yet, but yeah, there we go. Perfect.
Okay.
All right, John. And in particular, I was just going to say we have a second example here, and everybody get ready because we're going to be talking about lizards.
All right.
John, that's your cue.
Thank you. So I hope you all appreciate it. You know, as in many aspects of research, we had to make some trade-offs, and there's an explicit one made between the number of subjects and the effect estimate, the validity of the effect estimate. And you know, oftentimes we worry more about validity than we do about the precision of the estimate. It's but you know, in your individual research, you have to make that trade-off, and you want to consider, is it worth that trade-off? There's a couple more slides before we get to the lizard example. Jeremy, should I present these about the celecoxib example? So if you were to do the comparison of celecoxib to non-specific NSAIDs, you would unadjusted, just comparing the original table, you would see an increased risk of GI bleed with celecoxib. But that increased risk is probably due to all of those differences in patient characteristics that we observed, that the people who who got celecoxibs were at higher risk to begin with for one reason or another. And if you adjust for age and sex, that's a partial adjustment. It takes care of a lot, but it doesn't take care of everything. You lower the odds ratio of GI bleed associated with celecoxib to 1.05, but it's still not protective, as the randomized trials had shown that celecoxib reduces the risk of GI bleed. And so when you go to a more extensive adjustment through propensity score matching, you end up with actually a little bit of a protective odds ratio for bleed with celecoxib. It's not statistically significant. The confidence interval includes a null value, but it's still suggesting that there's a benefit, a lower risk of GI bleed when you take celecoxib. So this slide is a simulation study conducted by Soledad Cepeda and colleagues, but the idea is that it's showing this point that I made earlier about you can build a richer model of treatment selection than you can of outcome occurrence. You can put more variables into predicting who gets treatment A and treatment B than you can into who gets a stroke or who gets an MI. And that richness allows you to account for more potential confounding variables. And so anyway, this is a point that's been made a number of times, but this is the actual sort of mathematical advantage that propensity scores have. There's, of course, a whole range of other advantages of propensity scores having to do with explicit identification of areas of overlap in the propensity score. That's a really powerful concept, and that's why we spent a lot of time on it, because it really helps you understand what it is that your analysis is comparing, and sort of the range of patients to whom your results can be generalized. So mathematically, this is the most important part of the value of the propensity score, is that you can build a richer model of exposure than you can of an outcome, so you can account for more confounding. Okay, and this is just saying it in a different way. So thinking back to our confounder triangle, if we address confounding by random allocation or by propensity score, we can get a more clear estimate of treatment effect on outcome. And that arrow between treatment effect and outcome can then be quantified. Okay, so now we can move on to the example. So this is moving away from the celecoxib example into a study of exenatide.
And I know everyone came to this course thinking, I hope they talk about lizards. And
yes.
And for all of you who came to the course thinking that, this next set of slides is for you.
Excellent. Okay, so just a quick summary. The idea of in doing a propensity score analysis is starting with some upfront causal work, thinking about the population, thinking about what kind of comparison you want to make, what's your exposure group and comparison group, and then identify factors that may be correlates of exposure, things that went into the prescribing decision. Then you build the propensity score, and then you use the propensity score to perform an outcome analysis. And we're going to talk about 5 different ways to use the propensity score. We've already talked about these briefly. Matching, we've spent time on, but the others, restrictions, stratification, modeling, and weighting, we'll also cover now. So this is a reanalysis of a paper that my colleague Dave Dorr and I worked on and published. This reanalysis focuses more on the propensity score methodology, but as part of the background, I'll talk about the clinical case and lizards, and then we'll introduce the different methods. Now, all of these analyses have been done using the same data set as was done in my original analysis with Dave Dorr, but done in Jeremy's shop using the ATN software. So here's the lizard issue. This is about exenatide. It's a drug for type 2 diabetes that is a glucagon-like peptide 1 receptor agonist, and it's originally was identified in the saliva of the Gila monster, and you see a picture of the Gila monster, which is a type of lizard that lives in the southwest part of the U.S. and in Mexico, and it's it has a saliva that is toxic, and one of the toxins that's been identified is this exenatide. I've heard that all the exenatide that's used pharmaceutically is synthetically manufactured, so no lizards were harmed in its production. But it's been demonstrated to be effective and reduces hemoglobin A1C. It also reduces body weight, but nausea and vomiting are very common adverse effects. They have adverse GI effects from exenatide. And shortly after it was marketed, there have been spontaneous reports of adverse effects, especially pancreatitis, that was related to exenatide initiation. There was a series of case reports that was discussed in the literature that found some patient characteristics. And here's a particular case report talking about a male who's 69 years old who had a long history of type 2 diabetes, started on exenatide subcutaneous injection twice daily, and other medications at that time were discontinued for diabetes. And shortly after, developed mid-epigastric abdominal pain that radiated to his back, and it intensified over a few days, and eventually was admitted to a hospital. And he's amylase and lipase, and these are enzymes that are present in the pancreas, and that when there's pancreatic injury or inflammation, as there is with pancreatitis, they leak into your bloodstream, and so you can detect them at higher levels than they normally are present. And so there's a marker that this patient actually has pancreatitis. And then CT scan also showed that there wasn't a gallstone cholelithiasis. And so the presumptive diagnosis was that this was acute pancreatitis. And so you have a case report like this, and now several case reports, so case series of patients who experience acute pancreatitis after they've been initiated on exenatide. And so the regulators asked the manufacturer to follow up on this. And so they contracted with us to do a study of the association between exenatide and acute pancreatitis. And so that's what we did. We developed a study in the Optum research database to assess whether exenatide initiation and use was associated with acute pancreatitis more than comparison other anti-diabetic drugs. We created a basket of other anti-diabetic drugs, and we had a baseline period. We wanted to identify initiation of either exenatide or these other anti-diabetic drugs, and then we follow patients after that initiation event. So this is a new user cohort design or inception cohort design of initiation. The acute pancreatitis itself, there's a sort of a clinical definition of acute pancreatitis, which is this inflammation of the pancreas, and it's associated with pretty severe symptoms, nausea, vomiting, and food intolerance. It can be caused by gallstones, and that's why in that case report they wanted to rule out gallstones. It can also be caused by acute or alcohol abuse and weight loss and various other risk factors, including diabetes. Diabetes by itself is a risk factor for acute pancreatitis, and also then more severe or uncontrolled or long-standing diabetes is a greater risk factor than earlier forms of diabetes. And so the identification of, or the underlying question is the association? Are these case reports that we observe in the literature and that had come to regulators' attention, are those just a function of how exenatide is being used, that is being given to patients with diabetes and patients at more severe forms of diabetes or longer standing diabetes that's not well controlled on their existing drugs? Or is it, so is it due to the exenatide itself, or is that those case reports just a reflection of the prescribing characteristics of exenatide? And just those people would have a higher risk of acute pancreatitis regardless of whether they got exenatide or not, and the exenatide is just serving then as a marker for high risk population. And so we set out to do the study to address that question. In the claims data, it's fairly straightforward to identify who gets exenatide and who gets the other diabetes medications. But then the identification of the outcome, the acute pancreatitis in the claims data, there's a very specific ICD-9 code for acute pancreatitis. And when it comes, from a hospitalization or an emergency department visit, it's associated potentially with actually having acute pancreatitis, and that's the code ICD-9 577.0. This study was done in the ICD-9 era, so now there's ICD-10 codes, and if we were to do this study now, we'd have to account for both ICD-9 and ICD-10. So we wanted to build a propensity score, and so to account for lots of differences in patient characteristics of who gets exenatide relative to the other diabetes medications. And we used a 9-month baseline period, and this is a trade-off. Often you see studies that have 6-month baseline or 12-month baseline, and we actually did a calculation to figure out how many people would qualify under 9 months, 12 months, or 6 months baseline period, and the 9 months sort of gave the best trade-off of number of patients and amount of baseline data. We had a set of predefined covariates as well as empirically identified covariates that included, investigation of the 100 most frequently used medications and diagnoses and procedures among patients who initiated exenatide and patients who initiated other drugs for diabetes. And then we built our propensity score using logistic regression that predicted exenatide as a function of those covariates. The 10 most predictive variables were also interacted with calendar time, because and this is as Jeremy mentioned earlier on in the earlier part of the lecture, is that interaction terms are pretty rare to find in propensity scores, and so that a lot of times we don't even think about interaction terms. But one of the big exceptions to that is interactions with calendar time. And I want to provide a little bit of intuition about calendar time, because calendar time is important in that as time goes on, medical practice doesn't stay static. So medical practice changes as time goes on. Just clinicians learn more, and there's literature that's published. And so the way they prescribe at one point in time may be different than the way they prescribe at another point in time. And what that corresponds to in the propensity score is that the coefficient or the weight associated with each of the patient characteristics, age and sex and comorbidities and other medications, is different at a different point in time. And so if you use a propensity score that's the same across that whole range of time, the covariate doesn't change. And so that's not reflecting the way medical practice is. One of the ways you can account for that is by building in interaction terms between those variables that might change with respect to the weights in different periods of time and calendar time. So you build in these calendar time interactions, and we chose the 10 most predictive variables based on univariate C statistic as the ones to build this interactions with calendar time is. The logic behind that was that people or variables that were less predictive than the 10 most predictive based on the univariate C statistic would have less change over time than those in the top 10. So that was why we selected only the top 10 to interact with time. And then we forced other pre-specified variables, the ones that the clinicians and had told us, this is what I use in prescribing. And we did stepwise selection to identify this. And we also, we wanted to exclude those variables that might have been sort of like the IV placement variable that I mentioned as a potential, variable that can be a problem because it reduces efficiency. It makes your groups less overlapping. So these top 10 variables were I'm listing them here. It's not super important. It's just these are what empirically came out as the most important variables that determine who gets exenatide relative to the other diabetes medications. And then as we move forward, we're looking at the characteristics, and we've graphically shown who gets exenatide and who gets other anti-hyperglycemic medications or diabetes drugs. And you can see that at different ages, there's different relative prevalence of exenatide initiation relative to other diabetes medication initiation, so that older people, the 65 plus category, tend to get other diabetes medication, and that it's really the younger people or middle age, 40 to 64, who seem to be preferentially prescribed exenatide. And then when you get to the really young 18 to 39-year-olds, it goes back the other way to other diabetes medications. And then males seem to be more likely to get exenatide than females. And then some other variables. You look at the number of prior diabetes medications. You see that there's more exenatide initiation with prior diabetes medication use, because that's consistent with exenatide being a later stage treatment than a lot of the other diabetes medications. So this helped identify that. The other is that there are other drugs that cause acute pancreatitis, or at least have been reported to cause acute pancreatitis in the literature, and so-called class 1 and class 2. And so it looks like exenatide is actually given more frequently to people who are on other medications that might also cause acute pancreatitis. So it's a good thing to account for in the propensity score. Here's our propensity score distributions. These are real data, and so you see the solid black line, although they're both solid, the thicker solid black line is exenatide initiators, and you can see that distribution goes out, from pretty close to 0 all the way past 0.9. And then the comparison group, this basket of other diabetes drugs, it's really shifted to the left, and it has a high peak and then a much lower tail. And so this is our survival curve for the occurrence of acute pancreatitis. This is before matching or before doing anything with the propensity score. Just wanted to show you what would happen if we were to compare Byetta or exenatide to other diabetes medications. It looks, as you can see, that Byetta is accumulating more acute pancreatitis events than the comparison other diabetes medication. That's sort of what, the fact that all these case reports were in the literature had shown, is that there seemed to be a higher risk of acute pancreatitis with Byetta, but this is not accounting for any of those factors that we know are important. And so if we do match on the propensity score, you can see now these are our propensity score distributions after match. They're right on top of each other. The solid or the thick black line and the thinner black line are right on top of each other. But now if we follow the matched cohorts, the occurrence of acute pancreatitis is almost identical in the two cohorts. And you have a pretty good sense that if you were to look at a hazard ratio or relative risk of acute pancreatitis, you would get something pretty close to 1. That two groups seem to have the same essentially the same occurrence of acute pancreatitis. And so accounting for all of the variables in that propensity score sort of removes the association between exenatide and acute pancreatitis. And this is just our paper. And so now I'm going to pass it over to Jeremy to talk through sort of the approach used to reanalyze it using not just matching. Now we're going to talk through some of the other techniques for applying or using the propensity score.
Okay. John, was that my cue?
That's your cue.
Okay. So we're going to talk about different ways to use the propensity score and to look at this data one more time. So we'll go to the next slide. Okay. Sorry, I lost the thread there for a second. Okay, so like many database studies, we started with a lot of patients here, and you can see in this database, there were 55 million patients. Sorry, before I just launch on this, John, did you see the question from Thibault?
Yeah, I'm just
seeing
it now.
And Manel has a question in the same vein, so let's definitely talk about this for a second.
Yeah, I mean, the calendar time question is important because it goes back to what we started with, the causal model and how you are going to apply it to your research. But certainly calendar time can be an instrument, and we've talked about how you shouldn't include an instrument in your propensity score, and so both things are correct. And also what I was saying is also correct, which is that medical practice evolves over time, and so you may want to include calendar time or calendar time interactions in your propensity score. These are not necessarily contradictions. At the extreme, for sure, calendar time can be an instrument, and I can give you the intuition around that. And if you imagine a time before exenatide was approved, before it was even on the market, then all of the exposure to diabetes medications would be non-exenatide exposure. And so you could conduct this as an instrumental variable analysis. You could say, let's compare historical data when exenatide was not available to post-exenatide data when exenatide might be used. And then you compare those two populations, and you have to worry about all the assumptions that are unique to instrumental variable analyses. But there may be other things that changed in those timeframes, and not just the fact that exenatide was available. But that would be an instrumental variable analysis. It's a comparison of a time or a setting where exenatide would not be used, and in a setting where exenatide would be used. And so that's the kind of thing where, well, if that's the case, you don't want to build that into your propensity score, because you don't want to have the time before exenatide was available in your propensity score. But what I was talking about is this idea that the medical practice is not static, that the weight that somebody applies in prescribing exenatide in the early time when exenatide is available may be different than the weight that's applied to, say, age or sex or some of the other covariates in a later time, once more prescribers are using exenatide, and once they become more familiar with using exenatide, then it changes how they select patients to get exenatide. And so I think you have to be careful with using things like calendar time or region that are often used as instrumental variables, or preference. Preference can be another instrumental variable. These kinds of variables can be problematic if used in the propensity score, but the calendar time example also shows where they can be beneficial. And so it's about understanding what it is that you're doing and making sure it matches your starting causal understanding of the data.
Yeah,
Anything
and
else?
that line between confounder, effect modifier, and instrument is like how do I say it? It's like so clear in your first epi class that you take, and then I'd say becomes gradually sort of less clear over time in some cases. And so think again, like John was saying, that where we're talking about effect modification here, we're talking about effect modification of the treatment choice process, not the treatment effect. And so, when we're talking about interaction terms here, it's things that would modify the treatment choice process, and calendar time can be one of those. Okay, so John, can you go back just 2 slides? So we're going to be looking at this question, one more, if you don't mind. This question of pooled analysis of exenatide use, risk of acute pancreatitis. We're going to reanalyze the data in a way similar to what John and Dave Dorr and others did in this paper. Our main measure on the next slide will be a Poisson regression to estimate adjusted rate ratios. We are going to use propensity scores, believe it or not, and we're going to use them, as John said, 5 ways. And also examine along the way diagnostics, and hopefully by the end we'll also get to a place where propensity scores went way wrong, one specific way of using propensity scores went way wrong, and how those diagnostics that we look at could have alerted us, or actually did alert the investigators, John included, to that situation. So much more to come. So like many database analyses, as I was saying before, there are a lot of patients that you start with, and you end up excluding the vast majority in your very first step here. So 55 million patients in this database, a little under 1 million of whom met the cohort entry criteria. We applied enrollment exclusions, prior use exclusions, multiple exposure exclusions, and history of pancreatic disease exclusions, and that led to about 203,635, give or take, patients in the final cohort. Okay, so a pretty typical kind of set of exclusions, a pretty typical kind of waterfall here. Okay, so on the next slide, taking a look at this patient population, similar to what we did with the COXIB example, where we look at differences between the treatment groups before matching, you can see some pretty strong differences. So differences in age, although that's hard to see with the categorizations of age, but differences, for example, in ACE inhibitor use, statin use, and other factors, and sort of the one question we need to answer is, do we think we can analyze the data without doing any further adjustment? And I look at a table like this and just scanning down the difference column, assuming these are all confounders, the answer is a clear no. We got to do something. Okay, so let's do something. We're all here to do something about this, right? If you look at this on an unadjusted basis, exenatide appears to increase the risk of acute pancreatitis by about 20%. But the confidence limit is super wide. And as John showed you on some of those prior slides, the number of events is very, very, very low. So this is a good case for propensity scores, because clearly there's a lot of things that we need to adjust for, but we also don't have a lot of outcome events. So if we were just doing a typical kind of multivariate model, that wouldn't work. But it's also going to be a challenge, because we still only have not that many outcome events. So wide confidence limits maybe are our destiny here, but we will see how that holds up over the next number of analyses. So unadjusted 1.2, file that away. Keep that in mind, because we will be looking at different ways of looking at that, but that's our starting point. Next slide.
There's a question in the chat about,
Oh.
we included age as these categories in the propensity score. And the question is, could we instead put it in as a continuous variable? How would you like to address that?
Yeah, so linearity confirmed with age. I'll just remind you that it's linearity or log linearity with respect to treatment choice probability, right? So it's as you go up by a year in age rather, there's sort of a stepwise increase or decrease in your probability of being treated with drug A versus drug B. It's a different scale than we're used to, but sure, if you confirm that's log linear roughly so, then absolutely age can be a continuous variable. You can also do the age squared trick. You could take logs of different variables. You can do all sorts of some other things here, but again, we have a lot of room to maneuver here because as you can see, there's 20,000 exenatide patients, 180,000, so a total of about 200,000 patients. So if we want to not have to make assumptions about age and rather just enter the 6 or 8 variables into the model, we have plenty of room to do that here, which is nice.
Okay, yeah, I think that's good. There's another question about, this is more of a study design than a propensity score question. It's about if you allow a person to enter the cohort starting one medication and then later on they initiate your comparator medication, would you include both, or how would you account for that?
Are you going to answer it?
Yeah,
that's a hard question. Sure.
Yeah, that's right. It depends on if your analysis is done at the person level or at the episode level, and there's a whole literature on preference for one or the other. We didn't allow subsequent initiation, so we identified people who initiated on their whichever was first within the time window, either exenatide or referent medications, and then we did the analysis as an intent to treat, following from that initiation forward over time. The follow-up was not that long, so that there aren't a lot of people who had subsequent initiation events. But if you do a really long study where there's a lot of switching, you might have to account for this another way.
Yeah, and there's some, as John was saying, there's some great designs that account for that. They weren't sort of the right choice for this particular study, but Charles, if that's an issue that you want to consider, certainly, there's some good ways to handle that. Okay, so 1.2. Multivariate adjusted, also strangely 1.2, but with some wider confidence limits. I wouldn't put any real kind of stake on the multivariate adjusted analysis, just given the number of confounders that we have and the incredibly small number of outcome events. It's just not a model that one could really kind of rely on in this case.
And it's a good setting then to use the propensity score when you don't have a lot of outcome events and you have a lot of potential confounders.
Yep. Okay, so now we need to do our basic first step, which is estimate the propensity scores. So we want to predict exenatide versus other anti-diabetic treatment. Remember that we're confining our universe to these 2 treatments. It's sort of like a clinical trial. We're going to use all of those baseline covariates that we measured, and we're going to get our fitted values, our propensity scores from that. The next slide. Now, kind of not always sort of recommended practice, capital R, capital P, to inspect the betas of your propensity score model, but sometimes, we get curious and we want to look, and so we do. It's not bad, but sometimes these betas can be sort of less interpretable than they appear. But what we're seeing is that being 65 greatly lowers your risk, am I getting this right, of getting exenatide versus other anti-diabetic treatments. Being in the Northeast, Midwest, South, or West region of the United States as compared to, I don't know what the referent group is here.
Unknown.
What'd you say?
The unknown.
The other increases your risk, so to speak, of getting exenatide. Neuropathy and retinopathy, this is more clinically relevant, also greatly increase your risk of getting exenatide. So Charlotte, to the point you made, there's something sort of interesting going on sort of within this population, but not specifically the focus of this study.
But those are markers of long-standing diabetes, so they might, suggest, it's being used as a later therapy for the diabetes.
Yeah. Now, I've been doing this for a long time, and I still have trouble with pronouncing the word cholelithiasis. I don't know why, it just doesn't roll off my tongue. But you'll see that the beta there is 0. And if we were doing this as a traditional outcome model, and we saw a beta of 0 with a confidence limit of essentially like negative infinity to infinity, or 0 to infinity, that's sort of bad news. The deal here, though, is that it's actually okay. And propensity scores as models are pretty forgiving, because again, we're not trying to interpret that beta. So the fact that the beta is 0 doesn't sort of change our understanding of the propensity score in any way. What we're trying to get is the fitted value, right? The predicted value. And so if the way you get the predicted value is you take the patient's input data, you multiply each of those input variables by the beta that you see here, or the log of the beta, you add all those things up, and then you take the XPIT of that value, you get a probability. This 0 here will contribute 0 to that. So while it's not ideal to have this 0, it doesn't change your predicted value in any way. And so it's not kind of dangerous the way it might be in some other kinds of models. John, that was a big batch of opinion. Do you agree with that, or?
Yeah, no, but you run into this all the time. And for example, in this cholelithiasis, which is clearly a risk factor for acute pancreatitis, but the fact that it's 0 here is this is your prediction of who gets exenatide versus other diabetes treatments. It doesn't go into that decision at all. At least in your population, empirically, nobody had cholelithiasis at that prescribing decision point.
Let's look at the next page of beta, see if there's anything interesting here. Yeah, different. I think this is prior use, right, John?
Yep.
Would reduce your odds of getting exenatide. So cholelithiasis, is it giving any information? I think no. Well, I mean, it's giving in the information that it didn't have information to give. I don't know. Maybe that's a cheat, but in terms of sort of the classical notion of information in the propensity score model, no, it's not really adding anything to the propensity score model. And have we adjusted for it? No, we haven't adjusted for it. We've essentially found a population in which there was kind of equal low amounts of cholelithiasis, and thus it didn't really figure into our scenario. So we didn't adjust for it, but we also, I think you could argue, we didn't need to adjust for it.
Yeah, you could drop it from your propensity score and it wouldn't affect the quality of adjustment.
Okay, so now you see some betas. Now the propensity score overlap, this looks very similar to what John showed before. We have our coloring that we said from the Coxib example. The red patients here are the referent patients. The blue patients are the exenatide patients, and that purple zone is the overlap. And it's, again, you can see it was 20,000 versus 180,000. So actually, sort of just by chance, similar exposure prevalence, about 5%. As the Coxib example. So you have that propensity score that's really heavily shifted towards the left side. And if that bugs you and you want to sort of even out that distribution a little, there's some tricks to do that. Alec Walker has some interesting papers on ways you can even that out a little bit. The search term would be preference scores, right, John?
That's right.
It's a way to kind of center that distribution. So matching, we said 5 ways. I'm going to start with matching because everybody knows and loves matching, because we all learned about matching before the break. And if you match, you get a whole purple population, a red plus plus blue equals purple. And John, can you just go back one slide? The shape of that purple population is pretty close to the shape of that purple population in this slide, just kind of blown up because that's our entire population after matching. And maybe some of those corners got shaved off a little bit because we're doing 1-to-1 matching instead of 1-to-10 matching or whatnot. But roughly the shape that we'd expect. Okay. Let's skip this because I think we've talked about this already. So we looked at the characteristics before matching. Again, you know, magician says their magician thing, and we go to the next slide and we see what happens after matching. All of those differences, and maybe John, if you want to just cycle between those two slides a little bit, just keep your eye on the difference column. So forget the numbers themselves, just keep your eye on the difference column. Look at how all those differences between the groups just disappear like magic. But it's not magic because it's propensity scores. You know, you can tell your friends it's magic, that's okay. Now, unlike the Coxib example, John, can you go back one slide? Yeah, so look at the exenatide numbers here. So 19,809 patients in the exenatide group before matching. And if we go to the after matching, 17,558. So we lost, what was it, about 1,500 patients? Can you go back just so I can check my math? Oh no, we lost over 2,000 patients. We lost over 2,000 patients, which is, you know, roughly what, 10% or so of our treated group. And can you go back to the before matching overlap plot? Where are those 10% of patients being lost? Yeah, so the 10% of patients are being lost out in those higher values of the propensity score, because you can see there aren't a lot, right? But there are definitely treated patients, the blue patients on the right side of that plot, where there don't seem to be many, if any, referent patients in that same area. So when we're trying to find matches for those patients, we will fail out there. And those are the patients who will drop from our analysis. And again, we have to ask ourselves, is that okay? Is that not okay? You know, ultimately, it's a question of what are we estimating? Are we estimating the treatment effect of exenatide among all patients who get exenatide, or the treatment effect of exenatide among patients who could reasonably have gotten another anti-diabetic treatment? That's a study design question, but you can see how that design question sort of reflects analytically here. So it's a slightly different question that we can ask, but when we're doing this matching, we're looking at this ATT, the average treatment effect in the treated, meaning among patients who could have gotten either drug, what is the treatment effect in that group of patients? It's not the same as among all patients who got exenatide. John, you want to add anything before I move on here?
You know, it's an important point. We've lost relatively some of those higher propensity score patients who got exenatide because you couldn't match them. But if you look at this matched figure, there is at least some representation across the entire propensity score range. And that should be reassuring to you as a investigator, because if, for example, you're interested in seeing what would happen, you know, for the really clear candidates, the high propensity score, you can actually do subgroup analyses that look at that and see if there's heterogeneity of treatment effects, so that people who are the best candidates, do they have a worse risk of acute pancreatitis than people who are sort of the marginal candidates at the low end of the propensity score? And if you do see some kind of heterogeneity, that might suggest opportunities to create a warning on the exenatide label, saying don't prescribe it to people with these characteristics that would make them sort of the marginal candidates. But at least what the propensity score matching does is that it doesn't blind you to some region of that propensity score distribution, because all of it is represented here. That's not always going to be the case. And sometimes when you do the matching, you actually do drop out an entire range of the propensity score, so you can't even see what would happen in that range.
So John, let's go forward to slide 83. We'll pick up from there. So we used matching. We got rid of a lot of those differences we would, if this were a, quote unquote, real study, it was a real study, but
It was a real study.
But if we were, quote unquote, doing that, quote unquote, real study in this, quote unquote, class, we would stop and examine our balance very, very carefully. And that's a big point, which is that, we're definitely not encouraged to iterate on outcome models. That should be defined a priori, write your protocol, but iterating on propensity score models in order to get better balance, that's good practice, not bad practice. So we would spend quite a bit of time with that table one. John, I keep talking about this, maybe just put it back up. I think it was 2 slides before. Yeah, we'd spend quite a bit of time with this table to make sure that we had balance on the most important confounders, all confounders if possible. But again, as the same gentleman who told me that all data are precious, he told me not all confounders are created equal. So we would prioritize balance on, hopefully we get everything, but if we didn't get everything, we would prioritize the most important confounders, and that comes from knowledge of the situation.
And there's a question in the chat about this topic, which would be, if you were looking at this table one after matching and there's some variable that's out of balance that you think might be an important confounder, what would you do about that?
You stop and you deal with it. So one way to deal with it is to deal with it like we would with in a multivariate situation, where you get as best balance as you can in this matched data, and then you adjust for it further in your outcome model. So you can do kind of a doubly robust approach to adjusting for that confounder. You might want to restrict your population in some way such that you're able to get balance even without being able to achieve perfect balance on that confounder in the whole population. There's a dozen different ways you could handle it, but the important thing is that you choose one of them and do it, because not doing that leads you to a biased result, and that's obviously not our goal. Does that answer your question, Thibaut? So propensity score matching gives you an if no association. If post-hoc well, I that's complicated. If you go back again to first day of epi class, where everything is super clear, right? A confounder is something that to have an association with the exposure and an independent association with the outcome, right? And so in theory, your list of confounders, even if empirically it doesn't appear to be a confounder. The reality is obviously a little more complicated than that. So, if you believe it to be a confounder, but your population is constructed such that there is no association, maybe a exclusion criterion that you applied focused the population such that that confounder ended up having no association, like it would in a broader population. It's a call, but it's a subjective call.
Yeah, confounding is an inherently quantitative phenomenon, and so to think about it in purely quantitative terms is great. You can say, well, it's having a really small effect, so it's a confounder, but that small effect that it's having is not material to my analysis, and so I can when you have that sort of situation, you may it may change what you do with that confounder relative to a confounder that's clearly having a big effect. It's so.
Yeah, and Thibaut, like the only sort of danger here is, maybe on a univariate basis, it doesn't have an association, but in combination with some other something, right? Like there's sort of ways that associations can arise, and sort of best practice would be to go back to your DAG, right, and figure out whether you still believe you have an association, sort of given everything else that's going on in your study. But again, this is there's some pragmatic ways of working through the situation as well. Stratification. So like John said way back when, it seems like years ago, but it was only at most 3 hours ago. you can think of propensity score like any other variable, and a great analog is age. If you multiply a propensity score by 100, you're kind of in the 0 to 100 range. That's kind of sort of where the age variable is, in that 0 to 100 range. And if you wanted to adjust for or deal with the effect of age, you could stratify your population by age. Maybe it's 5 strata, maybe it's 10 strata, maybe it's 50 strata, right? But you could stratify by age. And so you can actually do the same with the propensity score. And in fact, in the Rosenbaum and Rubin paper, this was the initial proposed use of the score. Stratification has, when you're dealing with multiple covariates, the same sort of inherent exponentiality problem, dimensionality problem as matching, right? You end up with very many strata if you're stratifying by multiple variables, and many of the strata will end up being empty. And in particular, if you have a stratum that has an exposed patient but no referent, or vice versa, you have information to give, but that information will not contribute to your analysis. So propensity scores to the rescue here. You can stratify by the propensity score. And if you go to the next slide, the first question is, well, how many strata do I do? This kind of, relatively speaking, sort of ancient paper, although it really, kind of in the grand scheme of things was only 50 years ago, looked at number of strata and how much bias is accounted for by adding additional strata. And like many things, it's diminishing returns. And the kind of bullet is on the left side here. 5 strata will remove about 90% of the bias from the stratifying variable, which in this case is the propensity score, and the propensity score is a summary score. So it should kind of on average remove about 90% of the total bias. And you can see that in the table here under number of subclasses 5, 89.1, 0.6, 0.7. But if 90% isn't what you want, you can go to 10 strata or 20 strata. I think kind of effectively quintiles and deciles, so 5 strata or 10 strata are what I tend to see. But there's no reason that in theory you couldn't go beyond that. But as you increase strata, you have that problem of 0 cells. So as you start stratifying too finely, and you get exposed patients in one group and no exposed patients in the other group, or vice versa, then you start losing information, and you've reduced your efficiency and effectively thrown away data. And remember, all data are precious. So distributions, I think we've seen this. If we were to stratify this distribution by by quintile of propensity score, we would take all of the propensity scores that we observe in both the treated and untreated, and run it through a function in R or SAS or Stata to chop it into quintiles. In this hypothetical distribution, you have a kind of a wider stratum for stratum 1 and a wider stratum for stratum 5, and that's because the bulk of the data is kind of more in the center of this distribution. So you get kind of thinner quintiles or deciles, because you remember those are defined by number of patients. So we'll have the equivalent number of patients, but wider variation in propensity score. And in theory, this should get roughly 90% of the bias. But I would worry a little bit, maybe not worry, but I would wonder a little bit about stratum 5, which includes everybody from propensity score 0.67 all the way up to 1, and maybe wonder a little bit about stratum 1, which has that same problem, but just going the other direction. But it's a decent thing to do. Now in the real data here, you can see that the strata are sort of they're extraordinarily small on the left side. Remember, because that's where all of our patients are, because the exposure prevalence is 5%. So everything is kind of shifted towards the left, and very, very wide on the right side. So roughly 0.28 all the way up to 1 is the 5th stratum here. So again, this is it's okay to iterate. It's okay to look at this. It's okay to even say run a table 1 per stratum. let me see if I have balance per stratum, because that's the idea, right? Is that if you look within stratum, you should have balance because your propensity score is a balancing score, and it's okay to look. And in fact, that's a good thing to do to see if you actually achieved the balance that you intended to achieve through this technique. So what I put here are two summary scores of balance. One of them computed all the way through, the other one didn't quite, but I'll explain the scores to you. One is mean absolute standardized difference. So that means if you took age in your exposed group and age in your referent group, and you standardized age, which means you divided it by the standard deviation in the whole population, and you looked at the mean age in one group standardized, the mean age in the other group standardized, and you subtracted the two and took the absolute value, you'd have a mean absolute standardized difference for age. You can do that not just for age, but for every variable together. No, I should have said you would have an absolute standardized difference for age. You can do it for every variable, take the mean of all of those and have a mean absolute standardized difference for every variable. And if you had perfect balance, those would all be zeros. But they're not all zeros. You'll never have perfect balance, but a lot of them approach zero. So decile 6, decile 8, decile 9, decile 10, are pretty close to zero. But decile 1, decile 2, a little bit wider. And we can a priori set a cutoff and say if we see a mean absolute standardized difference in any decile or quintile greater than X, we will say we will do not have balance, we'll stop, reassess, and take appropriate action. So a priori, we should define kind of what our expectation would be, but we are, I'd say, within bounds to iterate in order to improve that before we go on to our outcome analysis. A C-statistic can also be useful. A C-statistic, remember, is the area under the curve. And the question here is, can I predict exposure versus referent within the decile? And within a decile, if I have balance, I should not be able to come up with a predictive model for exposure versus referent because I have balance. It's the same idea as if you try to come up with a predictive model of exposure versus referent in a randomized trial, you won't be able to because there was no association between those things to start with. Here we've created that low association by construction. And if we were to have no association, we'd see a C-statistic of 0.5. That means can't tell one from the other. It's essentially a flip a coin situation. And 0.6 means still pretty low. And so I'm pretty comfortable with this, like, not 1,000%, but I'm pretty comfortable with this as a way of looking at the data. And as I said, the diagnostics here are really important, and spending the time up front examining the data, examining the diagnostics, diving into each of these deciles. Oh, the difference seems a little higher in decile 1 or decile 2. Who's there? Like, who are these patients? Is there anything in here that's surprising to us? Like, that is, I'd say, good practice to understand your data. And again, you do this all with the outcome put away. So in no slide that I've presented, since John handed the baton back to me, have we talked about acute pancreatitis. That hasn't come up. We've been talking entirely about confounders and the exposure and the propensity scores. But we'll talk about acute pancreatitis, shortly thereafter. Actually, that's not fair. I did show you some outcome models, but so I'm not exactly telling you what happened. But in the discussion, at least, we have not talked about acute pancreatitis. Now, file under kind of side benefits of using propensity scores. We talk about the assumption of no unmeasured confounding. We also make an implicit assumption in a lot of cases of treatment effect heterogeneity, treatment effect homogeneity, or kind of the sibling assumption there, which is that the average treatment effect is fine, and understanding the average treatment effect across the whole population, even if there is heterogeneity, is informative. But we can certainly examine treatment effects within deciles to see if there is treatment effect heterogeneity, and that's essentially looking at the subgroup of patients with low and small and ever increasing and then super high propensity scores. it's not sort of intuitively satisfying, right? Like it's hard for me to say like, oh my gosh, we have a treatment effect in this group of patients who are, fourth highest probability to get exenatide versus other anti-diabetic, and I wonder what's going on in that group. There isn't sort of a natural link to something like, our older patients seem to have a higher rate ratio, right? That has more kind of intuition to it, but hey, it's a way of examining a treatment effect heterogeneity if you're making a strong assumption of no treatment effect heterogeneity as part of the results of your analysis. John, I've been talking a lot. Do you have anything you want to add in here?
Yeah, just to reiterate what you were saying, the propensity score itself is, it's this summary measure of candidacy for treatment A versus treatment B, so it's and it incorporates lots of variables that may reflect underlying biologic mechanisms for effect measure modification or heterogeneity. And so for example, as I was saying, that just the phenotype of somebody, say in this propensity score decile 10, the top is 10% of the propensity score distribution may be very different than the phenotype of somebody in propensity in decile 1 or 2, and that those phenotypes, the set of characteristics of a patient in those deciles, reflect the prescribing and so that and candidacy for treatment. But you couldn't use that information to say, create a warning in the label, say, don't give to the top 10% candidates. You'd have to identify specific characteristics of a patient. Don't give it to older patients, don't give it to males, or whatever the set of characteristics are that define that phenotype. But as a diagnostic, looking at these, the heterogeneity according to candidacy makes a lot of sense. This is a very natural sort of metric on which to assess heterogeneity, because clinicians may think in those terms of saying, this is a low probability candidate, this is a high probability candidate, and so that and the idea is also clinicians have a sense that if you give a drug to the best candidate, you should get the best outcomes from that treatment selection decision. And if you give a drug to a marginal candidate, you shouldn't expect a lot. And that's sort of a common expectation. This is a way to assess, is that actually the case? Do I see a different effect if it's given to the ideal candidate versus the marginal candidate? And so this is a very useful kind of diagnostic.
And that leads us very nicely. First of all, let's take a look at the treatment effect. I think it's 1.14. Again, still wide confidence limits. And I'm not focused on the treatment effect here because, as you can tell, that's sort of not the point. We want to talk about the propensity score process here. But this notion of ideal candidate and non-ideal candidate, that leads us nicely into the next of our 5 methods. So we're going to be at number 3 of 5 here, which is trimming. And again, sort of go back to the intuition around age. If I don't want to have confounding by age, I can restrict my population to patients in a small age range in which there is no confounding. Now, that's probably extreme, but if I want to, if I expect that very young patients, for example, and very old patients may have a different treatment effect than patients who are kind of in the more center of the age range, then I might restrict to ages 18 to 65 or something like that. Look, these are just examples, but you can do the same thing in the propensity score zone. And age again has this natural intuition around disease process, right? Propensity score doesn't have that same natural intuition associated with it, but we did have an intuition a while back, which is that patients who have a propensity score that doesn't overlap with patients in the other group, meaning there are treated patients who don't overlap with referent patients, or there are referent patients who don't overlap with treated patients, that there might be something different going on. And if you remember way back the discussion we had over the chat about what could be going on in the tails that would drive sort of strange behavior in the tails. If you zoom out a little bit on that discussion and say the tails of the distribution might just be different than the center of the distribution, and patients in the tails might just be different, and maybe we'll get kind of a better estimate of our treatment effect if we focus on patients more kind of towards the center of that distribution, and hopefully eliminate sort of any anomalies that may have crept in by doing that. That's when trimming comes in. And what you can see here is that it's a pretty simple process where you chop part of the distribution at the bottom and chop part of the distribution at the top from your analysis. You lose patients in doing that, right? So we're sort of in between matching where anybody who doesn't overlap gets dropped, and stratification where everybody's included. This is sort of a middle zone, but we're hopefully focusing the analysis in some sort of useful way. Now, this is called symmetric trimming because we trimmed equivalently on both sides. You could also, I think on the next slide, John, you had asymmetric trimming, right, where you determine your cutoff points by percentile, and you can look at it across the entire group, or you can look at the treated and the untreated different. There's a lot of different ways to do it, and Sturmer et al. Have a great paper in AJE from it's 10 years ago now about the different ways of doing this. But the intuition, kind of no matter how you implement it, is the same, which is that you're looking to create kind of more homogeneity within your patient groups before you move on to the next step, and that next step is generally stratification. So you trim, then you stratify the remainder of the patients. So here's in our exenatide example what it looks like to trim 5%, which is 2.5% from either side. So we'll lose exactly 5% of our patients here, but you can see we'll trim this tiny part of the distribution on the left where there are treated patients, the blue patients, but see that little gap, little tiny gap between the y-axis and the referent bar that's shooting up there. There aren't a lot of referent patients over there, so that will get trimmed out. And then we'll trim out the last kind of 0.09 here, from 0.91 to 1.0 on the propensity score scale, where there's some treated patients but almost no referent patients. So it's not as extreme as matching, where we trimmed to the purple zone basically, right? But it's also not as permissive as just pure stratification, where everybody was included, no matter what. And so if we go on the next slide, if we do that, where we trim 2.5% from either side for a total of 5%, stratify with deciles the remainder of the data, look, it doesn't change the treatment effect a lot, but again, we're looking for the intuition here about what we've done to see whether we think we've improved the quality of this inference. So that was 3. So we've done matching, we've done stratification, we've done trimming / restriction. Now let's do 4, which is regression adjustment. And this one's easy, like super easy. Throw the propensity score in your outcome model, done. So, again, sort of using the age analogy, we could run a logistic regression model here where we have an intercept plus a beta for our treatment plus a beta for age. And at that point, we've adjusted for age. We can do the same thing by putting our expected value of treatment, the E of X, which is our propensity score, into the model. We get a beta for the propensity score, and maybe we've adjusted for propensity score. The sort of intuition thing sort of comes back to bite us again here a little bit, which is that you could ask me and I would probably have an opinion on, or at least I would know who to ask to get an opinion on, the relationship between age and whatever disease I'm looking at. So that's sort of a biological relationship. As I get older, I'm at higher risk for X, Y, or Z, right? I can have or develop an intuition around that. It's really hard for me to have or develop an intuition of the relationship between a disease and the probability of being treated with drug 1 versus drug 2, drug A versus drug B. That's a harder intuition to get. And it's not something that I probably will ever develop, right? And I need that intuition because you can see it here from the formula. I'm creating a log linear relationship between this variable and my probability of disease. So, I can argue that there's a log linear relationship between age and MI, say, right? It's hard to say that there's a log linear relationship between probability of receiving drug A versus drug B and MI. So I'm in the end, like I'm doing something that will likely work. It often works. And I could probably do something fancy like put propensity score and propensity score squared or something like that. I don't even know. Or I could use splines, or I can do something fancy here. But it's generally kind of not the recommended approach because that intuition just isn't there. And it's very hard to say that you've come up with the right functional form of the model when it's hard to kind of reason about it on this propensity score scale, if that makes sense. I'm going to pause for a sec because that was a lot, and we've covered 3 different methods in the last 15 minutes or so. Anybody have any questions that they want to put in the chat? And again, we'll take one of those awkward pauses. I will use the awkward pause to enjoy some delicious Dunkin' Donuts hot coffee. This propensity score course brought to you by Dunkin' Donuts. Just kidding.
Yeah, we're supposed to be careful with how much we use brand names during these skills courses.
Of medications or coffee company. So there's a question here from
it's coming.
It's coming. That's definitely not off topic, and we will cover that very shortly. And again, if I'm pronouncing your name wrong, just send me a direct message and tell me how to do it right. Because I apologize. Okay, so I've done regression adjustment with the propensity score once in my career. If you go back one slide, and that was because I was doing a simulation analysis, and this was for my graduate school thesis. And my simulation analysis required running, on the order of like 1 billion propensity score models. And so the amount of time it took per model was pertinent because that affected when I could graduate. And so this runs very quickly because it's a very simple model, and you're just putting one variable in the model, it'll fit very quickly. So it substantially decreased my time to graduation, and so it was an appropriate model in that case. But in other instances, I would not recommend this for all the reasons that I mentioned. And there's some literature, by the way, that says 99% of the time you're going to get it right. 1% of the time you may not. It's just hard to distinguish whether you're in the 99 or the 1. And I'm being a little flip about it with graduation time and such. There's other reasons I used it for my thesis, but again, I just don't see a great reason to use this in day-to-day practice unless your outcome is so rare that, say, categorizing the propensity score into 5 strata would break your outcome model. This is a way to get more efficiency in that very extreme case. Okay, so now we get to the last one. We'll skip this. We get to the last one, which is weighting, and weighting and standardization are cousins here. So, like with age, we can standardize by age. Here we can standardize by propensity score. And with all questions of standardization, you want to make one population look like another population. And you have to choose, what is that target population? What am I standardizing to? So in age standardization, maybe you're standardizing to the distribution of ages in the United States Census or the UK national statistics, whatever it might be. Here you're standardizing on a different scale, but you're doing the same thing. And so there are 2 and maybe a 3rd emerging way of doing standardization. And the difference between them is what you're standardizing to, and then what you can understand from what you've done through that standardization process. So the one that comes up frequently, in fact, it came up in the chat just 3 minutes ago, is inverse probability of treatment weighting, IPTW. An inverse probability of treatment weighting says that you're going to standardize by taking all patients and weighting that patient's contribution to the analysis by the inverse of their probability of treatment. And it's funny because we've been talking for 3 hours about the probability of treatment. We call that the propensity score. So we have this probability that we need right at our fingertips. And so the way that you do this mechanically is that in the treated patient, you say 1 over the propensity score. That's the inverse probability of being treated with drug A. In the untreated patients, you do 1 over 1 minus the propensity score because you need to get the right treatment in there. So it's a very, very simple way of weighting. And I believe on the next slide, no, we're going to do one more, and then I'm going to show this pictorially. And that's when it's all going to make sense. So just stick with me for one more slide before you throw your hands up and say, weighting doesn't make any sense. So what the IPTW weight will do is say, I want to take the treated population and make them look like everybody, the treated and the untreated together. And I want to take the untreated population and make them look like everybody, the treated and the untreated together. So what I'll get is I'm standardizing to my entire patient population under study. That's my target of standardization. So that's my US Census in this example. The second option here, SMR weighting, says I want to standardize my treated patients to look like my treated patients, because that's what I'm interested in. And to the extent that my untreated patients don't look like my treated patients, I want my untreated patients to look like my treated patients. So my weight for my treated patients is 1, because that's how you get treated patients to look like treated patients. You don't change them. My weight for my untreated patients is the propensity odds, which is the propensity score over 1 minus the propensity score. And that magically will, if I weight all my untreated patients with that weighting value, will get them to look like treated patients. And now, what does this all mean, look like? Let's look at the next slide. This is our same distribution in the top cell that we've been working with all day, except that there is now a yellow line, and the yellow line is the pink line plus the blue line. So that's everybody. And if I were to take my treated patients, the blue line, and weight them by their inverse probability of treatment, 1 over the propensity score, and my untreated patients, the pink line, and weight them by their inverse probability of being treated, I end up with this thing that's labeled IPTW on the left. And lo and behold, that combined population, treated and untreated, has the same shape as the yellow line, which was everybody. And similarly, if I do this with SMR, I take my treated patients and they look exactly the same, but I take that pink line of untreated patients and I kind of smush them down through down weighting them, most likely, to look like my treated patients. And now I have everybody looking like my treated patients. And because the distributions are the same, because I have the same distribution of propensity score, same distribution of age, remember, substitute age in, I can now make a fair comparison within that group. So that's the magic of weighting, and it is magical in some cases, but there are some places where it can go wrong. Now, there's other ways of doing weighting. There's really kind of an infinite number of ways of doing weighting. One way that's sort of intriguing is something called overlap weighting, where, remember, in trimming, we said, let's trim off the edges because there's something potentially strange going on in the edges. Well, another way of doing that same thing is weighting everybody towards the center of the distribution. So you get kind of your most average patients, your most kind of representative or common or whatever the word is. I don't have the right word with my tongue tip here, right? Those become the patients that are overrepresented in my group, and that way, kind of the average experience gets amplified and the unique experience gets sort of quieted down in my analysis. Again, this is all very much dependent on what you're trying to measure And we have a slide here. It's subtle, so I'm not going to address that specifically. Oh, except that it's on the next slide, so I am going to address that specifically. But before we get to kind of treatment effect measures and what are we actually measuring, John, do you want to jump in, or does anybody have any questions that you'd like to ask?
Yeah, I mean, a couple of thoughts. There's some other weighting approaches that are intriguing, such as so-called matched weights, where in effect you use everybody but re-weight to the group that you would have ended up with if you match, and that avoids one of the problems that people have with matching of losing subjects. But you get there not by actually matching, but by weighting. So it's an intriguing application of weighting. There's another one that I've seen that's really intriguing as well, where you can re-weight your observational population to look like a clinical trial population, so that you say, okay, here are the characteristics of patients in my clinical trial. Here's the ones in my observational study. They're different. Let's re-weight the observational one to look like the clinical trial patient, so that I can see if the effect estimate that I observe in the real world is similar or different than what I observed in a clinical trial. Okay, so then we can move to this subtle one.
Just do a quick pause for questions. So there was a lot of information that came at you guys in the last 25 minutes here. So quick pause for questions. Okay, well, the window isn't closed, so we'll keep monitoring the chat, but throw any questions you have in there. Here's an important one. What are we estimating? And I think this is underappreciated. We've talked about matching, we've talked about weighting, we've talked about regression. What are we estimating? There are two main estimates that people tend to talk about, the ATE and the ATT. So the ATE is the average treatment effect. This is the effect of the treatment if we were to treat everybody versus not treat anybody. And it's sort of a pretty broad estimate. And the other is the average treatment effect in the treated, which is the effective treatment among those patients, very much like those who are actually treated, meaning the effect of the treatment among patients who could reasonably have gotten either of the two treatments. And if you think about overlap and you think about matching, and you think about who matched and didn't match, you think about stratification and who was included, and you think about weighting, maybe this comes together in some way as you think about it. It's the question of, are we looking at the treatment effect in everybody, whether or not they were, quote unquote, eligible to get the treatment, versus are we looking at the treatment effect among those for whom there was a reasonable choice between A and B, and the choice between A and B wasn't kind of preordained in some way. And maybe you want to, kind of think about this in terms of safety and effectiveness. If in safety, maybe the most important thing is to understand what's the safety of the medication among anybody who could possibly take it, which is, anybody, I guess. In effectiveness, what's the effectiveness of the medication among patients where I will want to make an active choice between A and B. They're telling us different things. Neither is right, neither is wrong. They're just telling us different things. And if you go to the next slide, I'm going to sort of draw the line between which each of these methods gives you and the estimand that you get. So matching, because we make all the patients look like the treated patients, and we're trimming out, essentially, sorry, I'm overloading terms, but we're omitting anybody who didn't overlap. We get that ATT, the average treatment effect in the treated. Stratification, because we're using everybody, everybody's data contributes, we get that ATE, the average treatment effect in everybody. Trimming is sort of somewhere in between, right? It depends how we trim and how much we trim. It's a little hard to say. Regression, we're using everybody, we get that ATE. IPTW, remember that we're making each of the treated and untreated groups look like the whole population. You're getting an ATE. SMR, we're making the treated group stay the same while we make the untreated group look like the treated group. We're getting an ATT. So hopefully this isn't kind of TMI, too much information, but there is some subtle difference. I'm going to say this, and I hope this isn't overload. in the absence of treatment effect heterogeneity, meaning let's say the treatment works the same in everybody, the ATT and the ATE will be the same. Because whether I look in this group where there's a choice versus everybody, I said it was the same, it'll be the same. But in cases, I think more commonly where the treatment effect isn't homogeneous and there is treatment effect heterogeneity, then there may be a difference here. And it's important to pick an estimand that answers the question you're looking to ask, which is the drug safe? Is the drug effective? What's, like whatever that question is, pick a matching estimand that's going to get you the answer you want. And so, John, while I read these questions, well, John, do you want to try to answer these questions?
Yeah,
Let's try to put just a question first. That's probably going to help the most people.
Yeah, I have a sort of a clinical approach to thinking about this question about an example where ATE and ATT would be different, and then we can think about the reverse of that when they're essentially the same, and that is if there's a subset of your population who might, for example, we've used contraindication as an aspect of propensity scores to consider. That if there's a subset of the population who has a contraindication, typically the reason they have a contraindication is that the drug would be harmful if given to them. And so if you estimate the average treatment effect, that includes everybody. So in effect, it's giving the drug to people who have the contraindication as well as to everybody else in the population, and then comparing it to if you don't give the drug to everybody in that population. And that's a clinically very strange thing to ask. The average treatment effect, when there's a portion of the population who are contraindicated, why would you even worry about giving it to them? They have the contraindication. So in that case, the average treatment effect among the treated may be more relevant. Here's the people who don't have contraindications, who in practice actually do receive the medication, and then we want to see what is the effect if we basically don't give the drug to those people compared to if we do give the drug. And so it's the effect of the treatment among people who are candidates for the drug, who should get it. Whereas if you look at the average treatment effect, it's giving it to everybody. And so it's in that case, you might expect to be a fairly large difference between the average treatment effect, where you give it to everybody, including those with contraindication, compared to the average treatment effect among the treated, where you give it to only people without the contraindication. So that's sort of the intuition. And then what Jeremy was saying is if there's no treatment effect heterogeneity, then these two effects, these two estimands will be the same, the average treatment effect versus the average treatment effect among the treated. And that assumption of no treatment effect heterogeneity is also essentially saying there's no contraindication. That is, even people at that very low end of the propensity score, if they get the treatment, they have the same effect as people at the upper end of the propensity score distribution. In some medications that's probably correct, and in other medications it's clearly not. And so it's very specific to the clinical question and the specifics of the medication as to whether the average treatment effect is preferred or the average treatment effect among the treated is preferred.
If we had a poll function right now, we would say, are you more confused than you were 5 minutes ago?
Or 4 hours ago.
So that's your tacit acknowledgement by the instructors that this is a subtle topic, and one that's not doesn't have kind of easy answers to all the questions. But hopefully we've answered the ones that have been put in the chat at the very least. Our IPTW weighted analysis, our SMR weighted analysis are here. You'll see that the confidence limit shrunk on the IPTW. Let's come back to that because that's probably not real because we are manufacturing patients. And so if you don't adjust your confidence limits appropriately, you will get things that look more confident than they are, because it appears to the algorithm that there's more information than there is. But remember that information is coming through weighting, which may not be a fair source of information, at least statistically speaking. Okay. John, where do we go next? We're gonna do your should we go forward to 115? Or I guess we can look at the COXIB example.
Okay,
Let's
yeah, so
really briefly.
yeah, go ahead.
I want to get to 115. I love your story on 115 there. So we spent the time since break on exenatide. Let me show you how all of these things work in our COXIB example, which was our primary example before the break. If I were to decile my COXIB distribution, you remember it was still pretty left heavy, but nice overlap. I would see very low, approaching zero mean absolute standardized differences in each of the deciles, and pretty poor ability to predict exposure, especially in the higher deciles, maybe some ability in the lower deciles. So this is the same method we looked at just a few minutes ago, but just with a different example. On 112, is there treatment effect heterogeneity by stratum? I would ignore what's going on in decile 1. Again, this is a relatively rare outcome, so you get some pretty wide variability there. Decile 3, definitely ignore. But maybe some evidence of treatment effect heterogeneity, but nothing that really kind of jumps out at me. And if I put it all together, unadjusted, my hazard ratio for GI bleed comparing celecoxib versus ibuprofen or diclofenac was 1.73, so 73% increase apparently in the risk of GI bleed among users of COXIBs. And COXIBs, as you recall, are meant to prevent GI bleed, so that does not seem right. And indeed, if you adjust by age and sex, that already goes down to 1.05. And if you propensity score match on all the things that we measured, that goes down to 0.83. If you do a multivariate analysis, you get to 0.96. Again, there's a lot of variables and not a lot of outcomes, so that might not be the best thing to do. If you adjust by deciles of propensity score, you're at 0.94. If you trim and adjust by deciles, you're at 0.95. And I haven't talked about confidence limits at all, but I will in a moment. If I use regression, I'm at 0.96. If I use IPTW, I'm at 0.97. And look what happens when I bootstrap the confidence limit versus just trust what comes out of GLM. It widens, as it should, because again, when you're doing IPTW weighting, you're creating patients very frequently. When you create patients, it'll look to the model like there are more patients than there are, thus more information than there is. And so it'll be really, it'll underestimate your variance. And really, to get a good confidence limit, one way is to bootstrap it. And you see that confidence limit widens. SMR is probably which one thing is not like the other? Well, it's SMR and propensity score matched, which appear much lower than the rest, right? 0.79, 0.83. SMR is even significant even after bootstrapping the confidence limit. And that's, we could have a lot of reasons for that, but if you go back to that slide of what are we estimating, right? ATE versus ATT, the two that are different are the two cases where we were estimating the ATT, the average treatment effect in the treated, versus the ATE, the average treatment effect. And so one of these could be better than the other. I'm not saying, that there isn't kind of if I'm doing this study, I pick a priori which model I use. And it could be that there's one that's more right than the others here. But when I look at the variability, that doesn't kind of throw me off, because I recall that I'm actually measuring two distinct things, and expect that there may actually be some difference between those, if that makes sense. John, I want to get to 115 is my favorite example of things that can go wrong when you use propensity scores. And I think up till now, everything's gone right and it's been hunky-dory and everybody's happy. But things sometimes go wrong. And so.
Sure. Yeah, thanks for the lead up to this. This is a study I did a few years ago, but the idea was a study of dabigatran relative to warfarin. So two different drugs that are anticoagulants used to prevent stroke in patients who have atrial fibrillation, and this is a particular subset of atrial fibrillation that's non-valvular atrial fibrillation. And so we wanted to compare the results that we got using matching relative to those that we obtained using propensity score weighting.
And I'll just jump in, John, and say that at least at the beginning, Dorothy was on. It may have gotten too late European time, but Dorothy, if you're still on and can jump in, feel free to jump in at any point.
Okay, yeah, one of the authors other than me was present. Okay. So when we did the analyses, there's a number of different things that we did. I want to walk through briefly. We did the analysis both in market scan data and Optum data, and we looked at using it as treated kind of approach, that is censoring people when they stop treatment, and in ITT that just continued the follow-up under the originally matched group, as long as people were contributing data. And want to point to then the effect that you're seeing in, let's start in the top left, which is market scan and stroke. And you see 0.64, which is sort of showing that dabigatran had patients on dabigatran had lower risk of stroke than patients on warfarin, which is fairly consistent with the randomized control trials. Then major bleed, there's also at lower risk of major bleed at 0.78. But then when you look down at the IPTW estimate, and it's 0, and the very narrow confidence interval around 0. And then on major bleed, it's very low as well. And then we look down at the other SMR weight, which is 0.57. So SMR was very close to the matched analysis, but IPTW seems to be very different. I want to talk about IPTW max 4, because what we did there is we capped the weight to be 4, and that so that through the IPTW, some people have larger weights than 4, and we sort of semi-arbitrarily chose 4 as the maximum weight that we would allow, and so that some patients were standing in for 4. That is, you make 4 copies of that patient and say, okay, this is that's what a weight of 4 might be interpreted as, and that if you cap the weight at 4, your result is very close to the SMR weight. And I'm wondering, how could this possibly be? I worked with the analyst to make sure this was, that there wasn't any error, but the 0 that you see for stroke and IPTW without capping the weights, it was real. That is, the analysis was running correctly. And so we were really wondering what was going on. And so then we moved to looking at the distribution of weights. And what you see, there's one patient in the market scan data. And if you can read the scientific notation when you look at this, that one patient has a weight. These are the weights under the IPTW, weights under the max 4, and weights under the SMR approach. There's a person who has a weight of 7.5 billion, 7.5, plus e to the 9th. Yeah, so essentially 7.5 billion. So one person was basically, being upweighted, copied 7.5 billion times to, so that, that person then becomes very influential. Basically, whatever happened to that one person was driving the entire analysis.
And just to make the connection, right? 7.5 billion is like in the neighborhood of the population of Earth. So this one patient was standing in for every patient on the planet, roughly speaking.
Yeah, very, very influential. And so we wanted to we're concerned about this because one person driving the entire analysis doesn't seem fair, and that's part of what led to the capping at IPTW weights of 4. And when we do that, we saw that the effect measure that we got after capping at 4 was very similar to the SMR weight or very similar to the matched approach. So that this is the reason this happens is because IPTW is the inverse probability of the propensity score. And if a person with an extremely low propensity score actually receives treatment, their weight is 1 over that extremely low propensity score, and it can turn out to be a very large number, and that's exactly what's happening here. And so I think the main point of our paper was to inform researchers that they should at least check the weights, not prescribing what they should do with the weights if they see something out of bounds. That's really a researcher's choice, but at least check the weights and make sure you're not being deceived by one patient that's like this. All right.
So we'll do one more example application of propensity scores, and then we will call it a day, an evening, or a night, depending on where you are. I thank everybody who's been with us for the past 3 hours and 50 minutes, especially those in the, if I get this right, Eastern Asia, Southern Asia, Australia zone, where I think it's approaching kind of the middle of the night. So thank you for sticking with us. Historical controls with propensity scores. So this is a pretty well-known example, but I think a really interesting example of how propensity scores can be used in ways that we didn't even begin to talk about today. So this is blinatumomab, which is a leukemia ALL treatment versus historical standard therapy of adults with relapsed refractory ALL. And what they did was they combined, go to the next slide, I think it's on here. Yes, so blinatumomab, Blincyto, is a treatment for advanced ALL, generally in patients for whom no other treatment has worked. So it's a last line or very late line therapy. The investigators ran a phase 2 single arm study in which there was about a 43% response rate and median overall survival of 6 months, but they wanted to look at the relative benefits as well. So what is the improvement in survival or the change in response compared to standard of care? And so quoting the investigators, they say regulatory agencies recognize the option of using external historical controls to demonstrate new treatment efficacy for accelerated approval when a disease is rare, has no satisfactory treatment, and the new treatment appears very promising based on preliminary data. And so I think each of those criteria is satisfied here. So I'm just going to walk through their approach a little bit, and I've kind of highlighted in green some of the key points here, but there is a lot of text. But I just want to walk through this because I think it all adds up into something very, very interesting. So they found a historical data set, which they're going to use as a comparator to their phase 2 clinical trial data, single arm clinical trial data. The historical data set was pooled from European national study groups and large individual sites in Europe and the US. And if you dig into it, those are largely the sites that participated in the phase 2 trial. So it's the same sites more or less where the phase 2 participants are drawn from. So you're drawing from a similar population here. 2 analytical approaches were used. The first was a weighted analysis. Okay, good. The second was a propensity score analysis, believe it or not, which created a better balance between historical controls and blinatumomab treated patients with respect to important baseline factors, and that then enabled quantification of differences in outcomes between the 2 groups. This should seem very familiar because we've been talking about this for a while today. So on the next slide, the propensity score analysis was used to balance measured characteristics between patients in the blinatumomab clinical trial, remember the single arm trial, and patients in a historical data set drawn from real world or observational data. data from the clinical trial and historical data set were merged, and candidate covariates were selected based on good factors, right? Important factors. And they're including the availability in both data sets. So, essentially this is we measured all the confounders that were relevant. I'm paraphrasing. On the next slide, the estimated propensity score, i.e. the predicted probability of participating in the blinatumomab clinical trial if it were being conducted during the period of historical data and the implied versus receiving the standard of care, was assigned to each patient based on a set of covariates. The balance of the covariates between patients in the clinical trial and patients in the historical data set was determined both by regression modeling and by calculation of standardized differences, both of which we did earlier today. In the estimate of treatment effects, propensity scores were used to adjust for differences between patients in the Blina clinical trial and patients in the historical data set using IPTW methodology, which we have now covered. So you're all experts in this whole study design. And to address the potential of over-influence of IPT weights among patients with very low probability of participating in the clinical trial, this is the problem that John just walked us through, stabilized IPTW methods were also used, as well as trimmed IPTW and stabilized IPTW values, whereby outlier values were truncated to maximum non-outlier values. A long way of saying is they did a lot of the stuff that John just recommended in the dabigatran example. Let's look at it. So you actually have to go to supplemental table 5 to get this, but it's there. So this is before adjustment and after adjustment. And let's just look at age, just because it's easy to look at. Age 37 years in the historical data set before adjustment, 41 years on average in the clinical trial before adjustment, standardized difference 0.233. After adjustment, which means IPTW, age difference of a little more than a year, so 38.1 years versus 36.9 years. Standardized difference, very small. P-value for difference, not significant. And you can see that play out among the other variables here as well. Do the next slide. And if you look at the results, they show, remember that there was, was it 43%, I think, response rate, right? In the single arm. What they're showing is a hazard ratio of 0.52 for overall survival and an improvement in complete response as well. Pretty consistent between the 4 different propensity score weighting methods that they used: IPTW without adjustments, and then stabilized IPTW as well. And just in case anybody is curious, hazard ratio of about 0.5 for overall survival, 2 for complete response, roughly speaking. Shortly thereafter, on the next slide, a clinical trial was published in the New England Journal, and finding, let me see what we got here, hazard ratio 0.71, so I think actually within the confidence limit. Oops. The chemotherapy, yeah. Finding, let's just say, for the interest of time, largely consistent results. So ending on a bit of a strange note, but just wanted to show you the range of things that one can do with propensity scores. And the theme is, how do we create balance? And blinatumomab resulted in higher rate of event-free survival than with chemo. So how do we create balance? We can do that in our safety analyses. We can do that in effectiveness analyses where all the data is coming from the real world. We can even do that in analyses where we're combining data from different data sets. But ultimately, we can use this analytic technique to get to balance in places where we couldn't or didn't randomize. It is 2 minutes before the hour, 2 minutes before the half hour in certain parts of the world. I think we had 2 responsibilities today. One was to give intuition and some details around propensity scores. First responsibility, second responsibility is to end on time. So hopefully we have accomplished the first, and looking at the clock, I believe we've accomplished the second. I really want to thank you for your participation today. Thank you, everyone, for all the chatting that was done. And it's been a real pleasure spending the last 4 hours with you. John, would you like the last word?
Yeah, and hopefully it's been useful for you. That was one of our aims as well, is to make sure that you got something useful out of it. And we'll let you be the judge of that. But it's really been enjoyable to speak with you about something that we care a fair amount about, propensity score analyses, and how to do them correctly.
And you know where to find us. ICPE will publish our email addresses and such. So if further questions arise, please come find us. And John, I promise you the last word. You want to say one more thing just to.
Thank you all.